In the high desert of Arizona on a night in 1981, a young astronomer named Robert Kirshner sat in the control room of the 2.1-meter telescope at Kitt Peak National Observatory and watched the data come in wrong. The telescope had been pointed toward a patch of sky in the direction of Boötes, the herdsman, that ancient constellation sprawling across the northern heavens between Ursa Major and Virgo. There was nothing unusual about the target, nothing that should have set it apart from any other 3-degree square of the celestial sphere. The team, Kirshner, along with Augustus Umler Jr., Paul Schechter, and Stephen Schechtman, had been methodically gathering redshifts, measuring the velocities at which distant galaxies were receding from us, building a map of the universe's large-scale structure, one spectroscopic observation at a time. This was the painstaking, deliberate work of cosmology in the early 1980s. You pointed your telescope at a galaxy. You spread its light into a spectrum. You measured how far the familiar absorption lines had shifted toward the red end, the telltale signature of a universe in expansion, every distant object fleeing from every other as space itself stretched. Then you recorded the number, moved to the next galaxy, and did it again. Night after night, field after field, building up a census of the cosmos, galaxy by galaxy, redshift by redshift. The expectation was simple. The universe at these scales should look roughly the same everywhere you pointed. Not identical, certainly. There would be clusters here, voids there, the natural lumpiness of a cosmos still settling into its gravitational architecture. But the variations should average out. Point your telescope in any direction, sample a large enough volume, and you should find galaxies. Lots of them. Distributed in the familiar cosmic foam that was just beginning to reveal itself to surveys like this one. Dense knots where gravity had pulled matter together, filamentary bridges stretching between them, and modest empty spaces, voids, where the density dropped but never quite to zero. That night, the field in Boötes returned almost nothing. Kirshner would later describe the sensation as confusion before it became wonder. The first instinct, always, is to assume you've made a mistake. Something must be wrong with the equipment. A cable has come loose. The spectrograph is misaligned. The photographic plates were developed incorrectly. You do not look at the data from a well-understood patch of sky and see a hole in the universe and immediately believe it. You check your work. You check it again. But the equipment was working. The plates were fine. The measurements were sound. Where the team expected to find roughly 100 galaxies in that 3-degree by 3-degree field, they found 3. 3 galaxies, in a volume where 100 should have been. Kirshner and his colleagues stared at the numbers and tried to make them make sense. They ran the redshift conversions again, translating recession velocities into distances, building a 3-dimensional picture of where these few faint smudges of light actually sat in space. And when they did, a gap opened up in the map. It was not a modest void. It was not the kind of gentle underdensity that cosmological models happily predicted. A region a bit emptier than average, a trough between the crests of cosmic structure. This was something else. This was a sphere of emptiness stretching across tens of millions of parsecs. A region so devoid of galaxies that it seemed less like a feature of the universe and more like an error in the universe. A place where the cosmos had simply forgotten to put anything at all. The team published their discovery in a short paper in the Astrophysical Journal Letters that same year. The prose was measured, cautious, appropriately scientific. They reported the coordinates, they noted the redshift range. They recorded the anomalous sparseness of the field, but behind the careful language was the unmistakable vertigo of having stumbled onto something that should not, by any reasonable expectation, have been there. What they had found was a hole in the sky, and not just any hole, a hole so large, so empty, so improbable that it would take years of follow-up observations to confirm that it was real, and decades of theoretical work to begin to understand what it might mean. They called it the Boötes Void, though some, with a grimmer poetry, would come to call it the Great Nothing. To understand why the Boötes Void was so shocking, you have to understand what the universe is supposed to look like. You have to feel the norm before you can feel the violation. Start with darkness. In the beginning, or as close to the beginning as physics can describe, the universe was a hot, dense fog. Matter and energy were so tightly coupled that light could not travel freely. Photons scattered off electrons in an endless directionless diffusion. There were no stars, no galaxies, no structures of any kind, just a plasma, nearly uniform, expanding and cooling in the aftermath of creation, but not quite uniform. Embedded in that primordial fog were tiny fluctuations, regions just slightly denser than average, others just slightly emptier. These variations were almost inconceivably small, mere fractions of a percent above or below the mean density. But in a universe governed by gravity, almost is enough. Gravity is patient. Gravity is relentless. Over millions of years, those denser regions pulled in a little more matter than their neighbours. The richer got richer. The voids got emptier. And the universe began, slowly, to grow lumpy. By 400,000 years after the Big Bang, the cosmos had cooled enough for electrons to bind with protons, forming neutral hydrogen. The fog cleared, light was suddenly free to travel, and the universe became transparent for the first time. That ancient light still fills the sky today. We call it the cosmic microwave background, and its faint ripples preserve a snapshot of those primordial density variations, frozen in place just before structure began to form. From that moment forward, gravity took over. The denser patches kept accreting matter. The first stars ignited, then the first galaxies, small, irregular clumps of gas and young suns, nothing like the grand spirals and ellipticals that would come later. These proto-galaxies merged and grew, colliding, combining, building up ever larger structures over cosmic time. But the growth was not random. It followed a pattern dictated by dark matter, that invisible scaffolding that outweighs ordinary matter by a factor of 5 to 1. Dark matter does not emit light. It does not interact with photons. But it does feel gravity, and it clumps just as ordinary matter does, only faster, because it has no radiation pressure to slow it down. In the early universe, dark matter settled into a vast interconnected web, dense nodes connected by long, tenuous filaments, with great empty voids stretched between them. This is the cosmic web. It is the skeleton on which the visible universe hangs. Imagine it as a three-dimensional foam, not soap bubbles, but something vaster, wilder, more fractal in its complexity. The bubbles are the voids, regions where the density is low, where galaxies are sparse, where the pull of gravity has long since drawn most of the matter away toward the walls and filaments. The walls and filaments are the structures themselves, rivers of dark matter along which ordinary matter flows, condensing into galaxies, which themselves cluster into groups, which aggregate into superclusters, which trace out the filaments like lights along a distant highway. At the intersections, the nodes, sit the greatest concentrations of mass in the universe. Galaxy clusters containing hundreds or thousands of galaxies, each with hundreds of billions of stars, all bound together by the gravitational pull of a shared dark matter halo. These clusters are the cities of the cosmos, blazing with light, burning through their gas, evolving rapidly as galaxies interact, merge and transform. The filaments are the highways between cities, thinner, less luminous, but stretching for hundreds of millions of light years. They channel matter from one cluster to the next. In 1989, astronomers identified a filament spanning 500 million light-years, the Great Wall, as it came to be called, one of the largest coherent structures ever observed. But the Great Wall was only the first. Surveys since have revealed filament after filament, wall after wall, stretching across the observable universe in every direction. And the voids are the spaces between. They are the dark patches on the map, the places where the density drops to a fraction of the cosmic average. They are not empty in any absolute sense. There is still gas, still the occasional galaxy, still the faint hiss of the cosmic microwave background passing through. But compared to the crowded nodes and bustling filaments, the voids are desolate. They are the countryside of the cosmos, the rural expanses where nothing much happens and no one much lives. The cosmic web was first predicted theoretically before it was observed. In the early models of structure formation, particularly those that assumed hot dark matter, particles moving at relativistic speeds in the early universe, matter was expected to collapse first into sheets, then into filaments, then into nodes. This top-down scenario predicted exactly the kind of filamentary structure that surveys would later reveal. By the time large redshift surveys began mapping the galaxy distribution in the 1980s and 1990s, the web was unmistakable. The Sloan Digital Sky Survey in particular mapped millions of galaxies and produced breathtaking images of the cosmic foam, clusters glittering at the intersections, filaments threading the darkness, voids yawning between. And it was against this backdrop that the Boötes Void emerged. The cosmic web made sense. It was elegant. It was predicted. It was observed. But the Boötes Void was something else. It was too empty, too large, too spherical, too much like a hole punched through the fabric of the universe, a place where the web had simply failed to form. The term cosmic web itself would not be coined until 1996, when astrophysicist Richard Bond gave a name to what surveys had been revealing for a decade. But even before the phrase existed, astronomers understood the pattern. They knew what the universe was supposed to look like, and they knew that the Boötes Void did not fit. Let us speak for a moment of geometry, of numbers, of what it actually means to say that a region of space is 330 million light-years across and almost entirely empty. The Boötes Void is roughly spherical. Its centre lies about 700 million light-years from Earth, in the direction of the constellation Boötes, that kite-shaped figure anchored by the orange giant Arcturus, visible from any dark site in the northern hemisphere. The void sits between two massive structures, the Corona Borealis supercluster at a redshift of about 0.8 and the Hercules supercluster at a redshift of about 0.03. It occupies a volume of space that, by any reasonable reckoning, should contain thousands of galaxies. It contains about 60 galaxies in a volume where 2,000 are expected. Less than 3% of the cosmic average density. Not a modest underdensity. Not a trough in the cosmic foam. A genuine absence. A place where the universe, for reasons still not fully understood, declined to build. 330 million light-years. The number is easy to say and almost impossible to comprehend. Light, travelling at its absolute limit of 300,000 kilometers per second, would take 330 million years to cross this void. Our entire species has existed for perhaps 300,000 years. Our entire planet has existed for 4.5 billion. The void spans a duration that dwarfs the age of complex life on Earth. It is a distance so vast that by the time light from the far side reaches us, continents will have drifted. Species will have evolved and gone extinct. Stars will have been born and died. But the better way to understand the void is not through time or distance, but through experience. Through what it would be like to live there. The astronomer Greg Aldring once offered a thought experiment that has since become the standard way of explaining what the Boötes Void actually means. Imagine, he said, that the Milky Way, our galaxy, our home, the 100 billion stars that make up everything we have ever seen with the naked eye, sat at the centre of the Boötes Void instead of in its current location. What would our night sky look like? What would our cosmology be? We would look out in every direction and see nothing, not just fewer galaxies, not just a sparser sky, nothing. No Andromeda smeared across the autumn constellations, no Magellanic clouds hanging in the southern hemisphere, no Virgo cluster, no Coma cluster, no Great Wall, no filaments, no cosmic web, just darkness, punctuated only by the stars of our own galaxy, which would still fill the sky, still trace out the Milky Way's familiar band, but would be utterly, terrifyingly alone. In this alternate universe, astronomers would develop just as we did. They would map the stars, measure their distances, work out the structure of our galaxy. They would understand that the Sun was one star among billions, that the Milky Way was a vast rotating disk of gas and dust and stellar fires. But they would see no evidence that anything existed beyond it. No island universes. No spiral nebulae whose distances could be measured. Just the stars and the dark. The Great Debate of 1920, that famous confrontation between Harlow Shapley and Heber Curtis over whether the spiral nebulae were part of the Milky Way or independent galaxies beyond it, would never have happened. There would have been no nebulae to debate. Edwin Hubble's 1923 discovery that Andromeda contained Cepheid variable stars, proving once and for all that it lay far outside our galaxy, would never have occurred. There would have been no Andromeda to observe. In the Boötes Void, we would not have discovered the existence of other galaxies until, perhaps, the 1960s at the earliest, when radio telescopes and increasingly sensitive photographic surveys might, just barely, have begun to pick up the faint smudges of galaxies at the void's distant edge. We would have spent most of human history believing, with perfect observational justification, that the Milky Way was the entire universe, that there was nothing beyond the stars we could see, that the cosmos consisted of a single galaxy, adrift in infinite emptiness, with no neighbours, no companions, no evidence that the universe had ever bothered to build anything else. This is what 330 million light-years of emptiness means. It is not an abstraction. It is not a statistic. It is an experience of cosmic isolation so profound that it would have reshaped our entire understanding of our place in existence. In the Boötes Void, we would have been alone in a way that is almost impossible to imagine from our actual position. Surrounded as we are by galaxies, embedded in filaments, part of a local group that itself belongs to a supercluster, that itself connects to the cosmic web stretching in all directions. We are not in the void. We are in the crowded heart of structure, and that accident of position, that sheer luck of cosmic address, is the only reason we know the universe is big enough to feel small. But Kirshner and his team did not know any of this yet. Not on that night in 1981, when the data from Boötes came back wrong. All they knew was that they had expected galaxies and found almost none. All they knew was that their careful measurements, their calibrated instruments, their years of training, all of it was telling them something that made no sense. The first paper was modest in its claims. It had to be. In science, the more extraordinary the result, the higher the burden of proof. Claiming to have discovered a vast region of cosmic emptiness, a void larger than any previously known, required more than a single night's observations. It required confirmation. It required other teams, other instruments, other lines of evidence. The confirmation would come, but slowly. Over the next several years, other surveys would turn their attention to Boötes. Other telescopes would gather spectra, measure redshifts, build up the three-dimensional map of that strange, quiet corner of space. And what they found, again and again, was the same thing Kirshner's team had found. Almost nothing. The void was real. It was not an error. It was not a gap in the data. It was a feature of the universe itself, a place where, for reasons that would take decades to understand, the cosmic web had failed to form. A place where the normal processes of structure formation had somehow stalled, reversed, or never begun. A place where 330 million light-years of space contained fewer galaxies than a single modest cluster in the dense heart of the cosmic web. By 1987, a fuller survey had mapped the void in detail. The boundaries were sharper now, the interior better explored. The team confirmed the coordinates, centered at right ascension 14 hours 50 minutes, declination 46 degrees. They measured the size, radius of 62 megaparsecs, diameter of roughly 330 million light-years. They counted the galaxies, about 60, in a volume where 2,000 should have been, and they gave it a name that would stick: the Boötes Void, or, for those who preferred a more poetic designation, the Great Nothing. The name was apt. In a universe defined by structure, by the grand architecture of the cosmic web, by the clustering of galaxies into ever larger aggregates, by the fundamental tendency of matter to seek out other matter and build, the Boötes Void was a place where that tendency had somehow been overruled. It was not merely empty, it was aggressively empty. It was a region that seemed to resist the very processes that had built everything else. And yet, even as the surveys confirmed the void's existence, they also began to reveal something else, something that would complicate the simple narrative of emptiness, something that would take years more to fully appreciate. The void was not quite empty. There were galaxies inside it, not many, not nearly enough, but they were there, faint, scattered, drifting through that vast expanse like dust motes in an abandoned cathedral, and they were strange. The cosmic web took shape over billions of years, and we have only begun to map it in the last few decades. But already certain truths have emerged. The universe, at the larger scales, is not random. It is not a uniform scattering of galaxies. It is a structure, a pattern, an architecture that reflects the physics of its own formation. Dark matter led the way. In the early universe, while ordinary matter was still coupled to radiation, buffeted by the pressure of photons, unable to collapse under its own gravity, dark matter was already settling into its web. It feels no electromagnetic force. Light passes through it. It interacts only through gravity, and through gravity it clumped. First into small halos, then into larger ones, then into the filaments and nodes that would define the cosmic structure. Ordinary matter followed. As the universe cooled and neutral atoms formed, as the radiation pressure faded and the fog cleared, ordinary matter began to fall into the gravitational wells that dark matter had prepared. Gas streamed along filaments, it pooled at nodes, it collapsed into dense clouds that fragmented, contracted, and ignited into stars. Galaxies formed, small at first, then larger as they merged with their neighbours, building up the massive spirals and ellipticals we see today. This process, hierarchical structure formation, is now the standard model of cosmology. It predicts the cosmic web. It predicts the clustering of galaxies. It predicts, in remarkable detail, the patterns that surveys have revealed, the filaments, the nodes, the walls, the voids. But it also predicts that the voids should not be quite this empty. In the standard model, voids form as matter flows away from underdense regions toward overdense ones. The gravitational pull of a filament or cluster draws matter toward it, leaving the void behind. But the process is never complete. Some matter always remains. Some galaxies always form. The voids should be underdense, yes, but not dramatically so. They should contain perhaps half or a third of the average galaxy density. Sparse, but not absent. The Boötes Void contains less than 3% of the average density. It is emptier than standard models predict, emptier than any void has a right to be. And that excess emptiness, that stubborn, inexplicable absence, has puzzled cosmologists for 40 years. Why is the Boötes Void so empty? The question seems simple. The answer is not. One possibility is that the void is simply a statistical fluke, an extreme fluctuation in the initial density field, a region that started out unusually underdense and grew emptier over time as matter flowed toward the surrounding structures. The cosmic web is vast, and in a large enough sample, extreme outliers are expected. Perhaps the Boötes Void is merely the far tail of a distribution, the cosmological equivalent of a 100-year flood or a record-breaking heatwave. But this explanation has problems. The void is not just extreme, it is too extreme. The initial fluctuations in the cosmic density field, as measured by the cosmic microwave background, were small, fractions of a percent. Growing a void this empty from such modest initial conditions requires either an improbably low starting density or some additional process that evacuated the region more efficiently than gravity alone. Another possibility is that we have underestimated how empty voids can become. The standard models of structure formation are built on simplifying assumptions: dark matter particles that interact only through gravity, ordinary matter that follows dark matter into its wells, galaxies that form wherever the density exceeds a certain threshold. But the real universe is messier. Galaxies form through complex processes involving gas cooling, star formation, supernova feedback, black hole jets, processes that can suppress or enhance galaxy formation in ways that simple models do not capture. Perhaps the Boötes Void is telling us that in the deepest voids these processes are different, that the lack of dense environments changes the physics of galaxy formation, that stars are harder to ignite, gas harder to cool, galaxies harder to build when there are no neighbours, no mergers, no tidal interactions to stir the pot. Or perhaps, and this is the most unsettling possibility of all, we have simply failed to see what is there. The human eye is a remarkable instrument, but it has limits. It can only see what shines brightly enough to register on its retina. In a dark room, objects do not become invisible because they cease to exist. They become invisible because they do not emit or reflect enough light for our eyes to detect. The object is still there. Our perception is simply inadequate. Telescopes extend our vision, but they do not escape this fundamental constraint. They gather more light than the naked eye, concentrate it, amplify it, record it on electronic detectors far more sensitive than biological tissue. But they too have limits. They can only see what shines brightly enough to distinguish from the background, from the noise of the sky, the glow of the atmosphere, the dark current of the detector itself. In astronomy, we call this surface brightness. It is a measure of how much light an object emits per unit of apparent area on the sky. A bright, compact galaxy has high surface brightness, a lot of light concentrated in a small patch of sky, easy to detect against the dark background. A faint diffuse galaxy has low surface brightness, the same amount of light, or even more, spread over a much larger area, diluted to the point where it barely rises above the noise. And here is the crucial point. For most of the history of astronomy, we have been systematically biased toward high surface brightness objects. It was not intentional, it was not a choice. It was simply a consequence of how observations were made. Photographic plates and later electronic detectors were designed to capture compact, well-defined sources: stars, galaxies with bright nuclei, quasars. The software that analysed the images was optimized to find peaks in the light distribution, bright spots that stood out from the background. Diffuse, low-surface brightness objects did not produce peaks. They were smeared across the image, blending into the noise, invisible to the algorithms that searched for galaxies. This bias was understood in principle from the early days of extragalactic astronomy. Astronomers knew that their surveys were not complete. They knew that there could be galaxies too faint or too diffuse to detect. But the magnitude of the problem was not fully appreciated until the 1980s and 1990s, when a handful of researchers began deliberately searching for the objects that everyone else had missed. What they found would reshape our understanding of what empty means. The night sky, even at its darkest, is never truly black. There is always some glow, the faint haze of scattered starlight, the soft luminescence of the atmosphere, the thermal emission of the telescope itself. Against this background, astronomers must distinguish the signal of distant objects from the noise of everything else. For a century, the instruments we built were optimized for one kind of signal: the sharp, bright peaks of stars and galaxies with concentrated light. We developed techniques to find these peaks, measure them, catalogue them. We became very good at seeing what was bright. But what about what was not bright? What about the objects that spread their light across such vast angular areas that they barely rose above the background? What about the ghosts? In the early 1980s, even as Kirshner and his team were discovering the Boötes Void, a British-Australian astronomer named David Malin was pioneering new techniques to reveal what traditional observations had missed. Malin worked at the Anglo-Australian Observatory, and his specialty was photographic amplification, methods of enhancing the faint, diffuse features in astronomical images that standard processing discarded as noise. What Malin found when he turned these techniques on the sky was a population of galaxies that had been hiding in plain sight. They were not small, some were as large as the Milky Way, or larger, but they were faint, so diffuse, so spread across the sky that they had been overlooked by every survey, every catalogue, every search for extragalactic objects. They were galaxies with surface brightnesses 10 times, 100 times lower than the familiar spirals and ellipticals. They were in a very real sense invisible, not because they did not exist, but because no one had looked for them in the right way. Malin called them low-surface brightness galaxies, and as the techniques improved, as other researchers took up the search, as new instruments were designed specifically to find them, the catalogues began to fill with objects that no one had suspected were there. The implications were profound. If the universe contained a population of galaxies too faint to see with conventional methods, then every estimate of cosmic density, every calculation of how much luminous matter filled a given volume of space, was potentially wrong. The Boötes Void might not be as empty as it appeared. It might simply contain a kind of galaxy that our instruments had never learned to see. This possibility would take decades to explore. It would require new telescopes, new techniques, new ways of thinking about what observation meant. It would lead to discoveries that would challenge everything astronomers thought they knew about the diversity of galaxies and the completeness of their surveys. But in 1981, none of this had happened yet. Kirshner and his team had found a hole in the universe, and they had no way to know whether the hole was real or merely an artifact of their own limitations. They had looked toward Boötes with the best instruments of their time, and they had seen almost nothing. The question that would haunt the field for decades, was whether almost nothing was the truth, or whether they had simply failed to see what was there. Whether the Boötes Void was genuinely, fundamentally empty, or whether it was full of ghosts, galaxies so faint, so diffuse, so different from everything in the catalogues that they had slipped through the cracks of every observation ever made. It is a question that, in some ways, we are still trying to answer. The Boötes Void remains one of the emptiest regions of the known universe. But empty, as we are slowly learning, is a word that depends entirely on what you are capable of seeing, and we have only just begun to learn how much we have been missing. In the control room at Kitt Peak, in the small hours of a night in 1981, Robert Kirshner stared at a map with a hole in it. The hole was real, the data was good, the instruments were working, and the universe, in that moment, became a stranger place than it had been before. There would be years of follow-up, years of confirmation, years of theoretical speculation and observational refinement. The Boötes Void would become famous, a landmark in the geography of the cosmos, a puzzle for cosmologists, a philosophical provocation for anyone who thought they understood what emptiness meant. But all of that was still to come. On that night, there was only the data, the confusion, and the first faint stirring of wonder. Something was missing from the universe. Something that should have been there was not. And in the absence, in that 300 million light-years of almost nothing, a question had begun to form, a question that would grow larger and stranger the more closely anyone looked, a question about light and darkness and the limits of what human instruments could see. What does empty really mean, when we can only see what shines brightly enough to reach us? The Boötes Void did not answer the question. It was the question. It hung there in the data, a sphere of silence at the edge of the observable universe, waiting for someone to figure out whether it was a real absence or only the shadow of our own blindness. The search was just beginning. The search was just beginning. But the discovery, as is so often the case in science, did not belong to any single team. 3 years before Robert Kirshner and his colleagues pointed their spectrograph at that puzzling patch of sky in Boötes, 2 other astronomers had already begun to suspect that the universe was not as uniformly populated as everyone believed. Stephen Gregory and Laird Thompson were working at the same observatory, Kitt Peak in the high desert of Arizona, and they were asking the same kinds of questions. What did the 3-dimensional distribution of galaxies actually look like? Not the 2-dimensional projections that had filled astronomical atlases for decades, but the real spatial arrangement, the depth, the distance, the structure hidden behind the flat plane of the sky. In 1978, Gregory and Thompson published 2 papers that would later be recognized as foundational. They had been conducting their own redshift surveys, measuring the velocities of galaxies to determine how far away they lay, and in the process they had noticed something troubling. There were regions of space that seemed to contain far fewer galaxies than they should. Not just slightly underdense, not just statistically sparse, but conspicuously, almost eerily empty. The term they reached for was void, a word borrowed from philosophy and everyday language, pressed into service to describe a phenomenon that astronomy had never properly confronted. Their papers were careful, methodical, appropriately hedged. Gregory and Thompson were not making sweeping claims about the nature of the cosmos. They were simply reporting what they had observed. Significant underdensities in galaxy distributions, regions where the expected population of luminous matter failed to appear. They suggested that these voids might be real features of the universe, not artifacts of incomplete data or observational error. They were, in essence, proposing that emptiness itself could be a structure, that the absence of galaxies might be as meaningful as their presence. The astronomical community received this work with polite interest and considerable skepticism. Voids were not part of the standard picture. The prevailing assumption was that galaxies were distributed more or less uniformly throughout the cosmos, with local variations smoothing out over sufficiently large scales. The universe was supposed to look the same in every direction, at every distance, the cosmological principle, the foundational assumption of modern cosmology. Voids, if they existed on any significant scale, would complicate that picture. They would suggest a lumpier, more uneven cosmos than the models predicted, and so the initial reaction was cautious. Perhaps Gregory and Thompson had simply surveyed an unusual patch of sky. Perhaps their sample was too small. Perhaps the underdensities would disappear when more data came in. This was not unreasonable skepticism. Science advances by doubting, by demanding confirmation, by insisting that extraordinary claims meet extraordinary standards of evidence. Gregory and Thompson had found hints, suggestions, preliminary indications. They had not yet produced the kind of overwhelming, undeniable proof that forces a field to change its mind. That proof would come 3 years later, from the Kirshner team's survey of Boötes. When the 1981 paper appeared in the Astrophysical Journal Letters, when Kirshner, Oehmler, Schechter and Schechtman reported finding only a handful of galaxies where they had expected to find 100, the astronomical community could no longer dismiss the idea of voids as a statistical curiosity or a preliminary suggestion. The Boötes Void was too large, too empty, too impossible to explain away. It crystallized everything that Gregory and Thompson had hinted at years earlier. It took their careful, hedged proposals and transformed them into an undeniable reality. And it did something else too. It gave the phenomenon a name, the Boötes Void, the Great Nothing. These labels attached themselves to the discovery almost immediately, spreading through the community with the speed of any good story. Astronomers are as susceptible as anyone to the power of a vivid image, a memorable phrase, a concept that captures the imagination. A void was striking enough. A void in Boötes, that ancient constellation, the herdsman, the ploughman, guardian of the northern sky, carried with it a kind of mythic resonance. And the Great Nothing had an almost philosophical quality, a suggestion that this was not merely a scientific puzzle, but something stranger, something that touched on questions of existence and absence that had troubled thinkers for millennia. Names matter. They shape how we think about things, what questions we ask, what assumptions we carry into our investigations. Calling this region a void implied that it was genuinely empty, that its defining characteristic was absence. But was it? Or was it simply a region where the galaxies were too faint, too diffuse, too different from the bright spirals and ellipticals that populated the catalogues? The name carried an assumption that would take decades to examine properly, and names also carry credit. In the sociology of scientific discovery, the question of who found something first, who named it, who gets remembered in the histories, these are not trivial matters. Gregory and Thompson had been there before Kirshner. They had seen the voids, described them, published on them. But it was the Boötes Void that caught the world's attention, the Kirshner survey that appeared in the textbooks, the 1981 paper that became the canonical reference. Gregory and Thompson's 1978 work was acknowledged, cited, remembered by specialists, but in the popular imagination, in the broad sweep of astronomical history, it was the Boötes Void that stood as the emblematic discovery. This is not unusual in science. Priority disputes, questions of credit, debates over who deserves recognition for a discovery. These are as old as science itself. Newton and Leibniz fought over the calculus. Wallace and Darwin divided the credit for natural selection. In astronomy, the history of discovery is littered with cases where multiple teams were pursuing the same question, arriving at similar conclusions through parallel paths, and the question of who got there first depends on exactly how you define the terms. What matters in the end is not the individual names, but the collective understanding that emerged. By the early 1980s, it was becoming clear that voids were real. They were not survey artifacts, not statistical flukes, not figments of incomplete data. They were features of the cosmos, enormous, underpopulated regions where the density of galaxies fell far below the cosmic average. And the Boötes Void was the largest, the most dramatic, the most troubling of them all. Troubling because it was not supposed to exist. The dominant model of cosmic structure formation in the early 1980s was cold dark matter, CDM, in the shorthand of the field. This model proposed that the universe's large-scale structure had grown from tiny density fluctuations in the early cosmos, amplified over billions of years by the gravitational pull of dark matter. Where the dark matter was slightly denser, it pulled in more matter. Where it was slightly less dense, matter drained away. Over cosmic time, this process had produced the web of filaments and clusters and voids that astronomers were just beginning to map. The CDM model was elegant, mathematically tractable, and remarkably successful at explaining a wide range of observations. It predicted that galaxies should cluster along filaments and at the nodes where filaments intersected, leaving voids in between. It expected the universe to be lumpy at small scales and smooth at large ones. It offered a coherent story of how structure had grown from the near-uniform conditions of the early universe to the complex hierarchical cosmos we observe today. But it had limits. It made predictions about what kinds of structures should exist and what kinds should not. and one of its predictions was that voids of the size and emptiness of Boötes should be extraordinarily rare, perhaps vanishingly so. The mathematics were unforgiving. In the CDM framework, the probability of finding a completely empty region depended on its size. Small voids were common, medium voids were less common, and truly enormous voids, voids spanning hundreds of millions of light years, should be so improbable that finding even one in the observable universe would be surprising. Finding one as empty as Boötes, with its density less than 3% of the cosmic average, was worse than surprising. It was potentially devastating. This was the tension that electrified the theoretical community in the years after Kirshner's discovery. The Boötes Void was not just a curiosity to be catalogued and set aside. It was a challenge to the foundational model of cosmology. If CDM was correct, then a void this large and this empty should essentially never occur. But there it was, hanging in the data, undeniable. The debates that followed were intense, technical, and often contentious. In Moscow, Yakov Zeldovich and his circle of theorists, some of the most brilliant minds in Soviet cosmology, grappled with the implications. Zeldovich had been thinking about voids for years, even before the Boötes discovery. As early as 1982, he and his colleagues were considering what they called giant volumes between superclusters, which were almost empty of visible objects, trying to understand how such structures could arise in the framework of known physics. The Boötes Void gave their theoretical speculations sudden, urgent relevance. In the United States, Jim Peebles and his collaborators were asking similar questions from a different angle. Peebles was one of the architects of the CDM model, a towering figure in theoretical cosmology, and he was not about to abandon his framework lightly. But neither could he ignore the data. The Boötes Void existed. It was measured. It was confirmed. The question was whether it could be accommodated within CDM or whether it required something new. New physics, new models, a fundamental revision of how we understood the growth of cosmic structure. The arguments played out in journal articles, at conferences, in the corridors of physics departments, and the late-night conversations that often matter more than the formal publications. Was the Boötes Void a mortal wound to CDM, or was it an outlier, a statistical fluctuation at the extreme tail of the probability distribution? Rare, but not impossible. The stakes were high. Cold dark matter was not just a model, it was the model. It underpinned virtually everything cosmologists believed about the universe's evolution, from the formation of the first structures after the Big Bang to the distribution of galaxies in the present day. If the Boötes Void could not be explained within this framework, then everything would have to be reconsidered. The textbooks would have to be rewritten. Decades of theoretical work would be called into question. And yet the void was there. 330 million light-years of almost nothing centered 700 million light-years away, containing barely 60 galaxies where 2,000 should have been. The observations were solid. The measurements had been confirmed and refined. Whatever story the theorists told themselves, they had to account for this impossible emptiness. The resolution, when it eventually came, was characteristically anticlimactic. Over the following decades, as observations improved and simulations became more sophisticated, cosmologists came to understand that the Boötes Void, while exceptional, was not impossible. It sat near the upper extreme of what CDM predicted, at the far edge of the probability distribution, but still within it. Voids of this scale should be very rare. The Boötes Void was very rare. This was uncomfortable, but it was not a contradiction. More importantly, the lambda CDM model, an updated version of CDM that incorporated the cosmological constant, the mysterious dark energy driving the universe's accelerating expansion, proved even more accommodating. In LCDM simulations, voids could grow larger and emptier than in the original CDM framework. The expansion of empty regions outpaced the expansion of denser ones, amplifying underdensities over cosmic time. The Boötes Void, in this picture, was not a violation of the model. It was an extreme example of a predicted phenomenon. This resolution was satisfying to the theorists. The models held. The framework survived. The Boötes Void could be understood as an outlier, a rare but explicable feature of a universe whose basic physics was well understood. But there was something unsettling about this conclusion, something that would only become clearer with time. The argument that the Boötes Void was compatible with, or not inconsistent with. The standard model was not the same as saying that the model predicted it. No one had looked at the CDM equations in 1980 and said, there should be a void of this size in this location with these properties. The void had been discovered first, and the theorists had worked backward to show that it could be accommodated. This is a common pattern in science, and it is not necessarily a problem. Models are frameworks, not crystal balls. They tell us what is possible, not what must occur. But there is a difference between a model that predicts a phenomenon in advance and a model that absorbs a phenomenon after the fact. The former generates confidence, the latter generates caution. And beneath the theoretical debates, a more fundamental question was lurking. The entire argument about whether the Boötes Void was consistent with, or inconsistent with, CDM depended on a crucial assumption: that we knew how empty the void actually was, that our surveys had accurately counted the galaxies inside it, that the figure of 60 galaxies, less than 3% of the expected number, was correct. But what if it wasn't? What if the void contained galaxies that our surveys had systematically failed to see? What if the apparent emptiness was not a real absence but an observational artifact, a reflection of our own limitations, our own biases, the particular wavelengths and sensitivities of the instruments we had built? This question, raised tentatively in the early years after the discovery, would become increasingly urgent as the decades passed. The Boötes Void forced cosmologists to confront not only the structure of the universe, but also the structure of their observations. It asked them to examine not just what they had found, but what they might have missed. And the answer, when it began to emerge, would be more troubling than anyone had expected. The surveys of the early 1980s were designed to find bright galaxies, the spirals and ellipticals that had filled the catalogue since Hubble's day. These were the objects that astronomers knew how to see, knew how to measure, knew how to classify. They were the building blocks of the cosmic architecture, the standard units of galactic accounting. When Kirshner and his team counted galaxies in Boötes, they were counting these familiar objects, using techniques optimized to detect them. But what if there were other kinds of galaxies, objects that were larger, fainter, more diffuse, spread out across such vast areas of sky that their light, though substantial in total, was smeared too thin to trigger the detection thresholds of conventional surveys? The possibility was not entirely new. Astronomers had long known that galaxies came in a range of sizes and brightnesses, but the full extent of that range, the existence of objects so faint and diffuse that they were essentially invisible to standard techniques, was only beginning to be understood. In the years after the Boötes discovery, as David Mullin and others developed new photographic amplification techniques, a hidden population of galaxies began to reveal itself. These were objects that had been there all along, lurking in the data, overlooked because no one had known to look for them. They were real galaxies, containing real stars, orbiting real centres of mass. But they were so dim, so spread out, so different from everything in the catalogues that they had slipped through every survey ever conducted. The implications were staggering. If conventional surveys had missed an entire population of galaxies in well-studied regions of the sky, regions that had been photographed hundreds of times, analysed by generations of astronomers, then what might they have missed in the Boötes Void? Perhaps the void was not as empty as it seemed. Perhaps it contained not 60 galaxies, but 600 or 6,000. Objects so faint that even the most careful observations had failed to detect them. Perhaps the great nothing was not nothing at all, but merely a region where the inhabitants were too dim to see. This possibility did not resolve the theoretical debates, it complicated them. If the true galaxy count in Boötes was unknown, if the observational errors were potentially enormous, then all the careful arguments about whether the void was compatible with CDM became suddenly uncertain. You could not compare theory to observation if you did not know what the observations actually showed. And so the Boötes Void became, in a sense, two puzzles at once. It was a challenge to our models of cosmic structure, an emptiness that pushed the limits of what those models predicted. And it was a challenge to our methods of observation, a reminder that the universe we saw was not necessarily the universe that existed. The data that filled our catalogues, the galaxies that populated our maps, the structures that we believed we understood, all of it was filtered through the narrow bandpass of our instruments, shaped by the particular sensitivities and limitations of the tools we had built. What did empty really mean when we could only see what shone brightly enough to reach us? The question had been implicit from the beginning. Now, in the years after the discovery, it was becoming explicit. The Boötes Void was not just a hole in the universe, it was a hole in our knowledge, a region where the limits of our observations and the mysteries of cosmic structure converged, where the boundary between reality and artifact became impossible to distinguish. The theorists continued to argue, the observers continued to refine their techniques, and the void itself remained, 330 million light-years of silence, a sphere of darkness at the edge of perception, waiting for someone to figure out whether there was truly nothing there, or whether we had simply failed to see what was hiding in the dark. The early 1980s were a pivotal moment. The discovery had been made, the debates had begun, the names had been assigned, the credit distributed, the implications recognized. But the deeper questions, the questions about what the void contained, what our surveys had missed, what emptiness truly meant, were still unanswered. Those answers would require new instruments, new techniques, new ways of thinking about observation itself. They would require astronomers to confront the possibility that everything they thought they knew about the universe's contents was incomplete, that the catalogues were not inventories but samples, that the maps were not territories but sketches, drawn with instruments that could only see certain kinds of light. In 1981, none of this had happened yet. The Boötes Void was a fresh discovery, a puzzle without a solution, a question mark hanging in the data. Kirshner and his team had found the hole. Gregory and Thompson had laid the groundwork. The theorists had begun their arguments, and the universe had revealed, in that 330 million light-years of almost nothing, that it was stranger and less certain than anyone had believed. The real work was still ahead. The search for what the void contained, or what it truly lacked, would stretch across decades. It would require telescopes that had not yet been built, techniques that had not yet been invented, insights that had not yet been imagined. But the question was now inescapable. The void was there. It demanded explanation. And in demanding explanation, it forced astronomers to confront not only the structure of the cosmos, but also the structure of their own understanding, the assumptions they carried, the biases they harboured, the limits of the light that reached their eyes. What does empty really mean? The Boötes Void had posed the question. The answer, if there was one, lay somewhere in the darkness, waiting to be found, or perhaps waiting to remain forever just beyond the reach of human sight. The years that followed the discovery were years of looking closer. If the void was real, and by the mid-1980s no serious astronomer doubted that it was, then the next question was obvious. What, exactly, was inside it? Not what should be inside it according to theory, not what the models predicted or the simulations suggested, but what was actually there, visible in the data, confirmed by spectroscopy and photometry, and the patient accumulation of redshifts. The void had been found. Now it needed to be mapped. The task fell to a generation of observers who approached the problem with the methodical care of cartographers charting a desert. They knew the boundaries, more or less. They knew the approximate centre, the rough diameter, the general coordinates. What they did not know was whether the interior was truly barren or merely sparsely populated, whether the void was absolute or merely relative, a true absence of structure, or simply a region where structure was thin and scattered and hard to see. The only way to find out was to look, galaxy by galaxy, redshift by redshift, building a census of whatever faint objects might be hiding in that enormous darkness. By 1987, a fuller survey had been completed. J. Moody, working with Robert Kirshner, G. McAlpine, and S. Gregory, published their results in the Astrophysical Journal, a systematic accounting of the sparse population that existed within the void's boundaries. The numbers were striking in their smallness. Where a region of comparable size in the general cosmic web might contain 2,000 galaxies, the Boötes Void contained approximately 60, less than 3% of the expected density, a structure 330 million light-years across, and within it, a population that could be counted without reaching 3 figures. But the most intriguing detail was not the total count. It was the distribution. The galaxies that existed within the void were not scattered randomly throughout its volume. They were clustered, arranged in a pattern that some observers described as filament-like. A thin strand of matter threading through the emptiness, a chain of faint light strung across the darkness. In the early catalogues, this chain numbered roughly 8 galaxies, 8 objects in a volume that should have held hundreds, 8 survivors in a desert that stretched across a significant fraction of the observable universe. The informal name came naturally, the chain. It was not an official designation, not a term that appeared in the formal literature with any consistency. But among the observers who studied the void, it became a shorthand for the peculiar distribution they had found. Those handful of galaxies arranged not in clusters or walls or the familiar structures of the cosmic web, but in a single tenuous filament, as if they were the remnants of something larger that had never quite formed. Herbert Rood was among those who tried to characterize this sparse population. The work was painstaking. Each galaxy required spectroscopic confirmation, a measured redshift that placed it definitively within the void's boundaries rather than in front of or behind it. The distances involved were enormous, 700 million light-years to the void's centre, and at those distances even a small uncertainty in redshift could mean the difference between a galaxy that was genuinely inside the void and one that merely appeared to be. The chain had to be verified, galaxy by galaxy, before it could be trusted. What emerged from this verification was a picture of almost haunting sparsity. The 8 galaxies of the early catalogues were real. They existed within the void's interior, not at its edges, not in the denser regions where the void met the surrounding walls of the cosmic web. They were genuinely there, hanging in that 330 million light-year emptiness, surrounded by nothing but darkness and distance. The census grew, but slowly. In 1988, Strauss and J. Hukra announced the discovery of 3 additional galaxies within the void. The following year, G. Aldring, G. Bothan, R. Kirshner, and R. Maske published a survey that added 15 more. The total crept upward from 8 to 11 to 26, but even the expanded counts remained vanishingly small compared to what theory predicted. The void was not quite empty, but it was as close to empty as the observed universe seemed capable of getting, and the arrangement persisted. The galaxies clustered near the void's edges in some cases, as if reluctant to venture too far into the emptiness. A small number of faint dwarfs appeared in the deeper interior, their presence suggesting either under detection, the possibility that many more such objects existed but had not yet been found, or remnants of some ancient process, survivors of mergers or failed structure formation that had left behind only these scattered fragments. The cylindrical region extending through the void's centre, the filament-like arrangement that observers had noticed from the beginning, remained the most striking feature of the interior population. It was as if the void contained not a random scattering of matter, but the skeleton of a structure that had never fully assembled, the ghost of a wall that had tried to form and failed, or the outline of a colony that had been abandoned before it could be completed. The question of origins haunted every observation. What were these galaxies? Where had they come from? Why were they here, in this particular arrangement, when the surrounding regions of space contained structures so much richer and more complex? The theoretical possibilities were numerous. Perhaps the chain represented the last remnants of primordial structure, a filament that had begun to form in the early universe, but had been disrupted by some process. A lack of dark matter, a deficit of the initial density fluctuations that seeded galaxy formation elsewhere. Some unknown mechanism that had prevented the void from filling in the way other regions had filled. Perhaps the galaxies were pioneers, objects that had formed relatively recently, and were only beginning to populate the void's interior, the first arrivals in a region that would eventually become as dense as anywhere else. Perhaps they were refugees, galaxies that had been flung into the void by gravitational interactions at its edges, wanderers cast out from the richer structures that surrounded them. None of these explanations was fully satisfying. The filament-like arrangement suggested structure, but the structure was so tenuous, so fragile, that it seemed impossible to explain by the same processes that had built the great walls and clusters elsewhere in the cosmos. The small number of galaxies made statistical analysis difficult. With a sample of 8 or 26 or even 60 objects, the uncertainties in any measurement were enormous, and the conclusions that could be drawn were correspondingly limited. The void's interior population was a puzzle within a puzzle, a mystery nested inside the larger mystery of the void's existence. What did it mean that these handful of galaxies existed at all? The question had no easy answer. Their presence proved that the void was not absolutely empty, that even in the most underdense region of the observable universe, matter had managed to collect, stars had managed to form, galaxies had managed to emerge from the darkness, but their scarcity proved that something had gone profoundly different in this region than in the surrounding cosmos. The same physical laws governed the void as governed everywhere else. the same forces of gravity, the same expansion of space, the same initial conditions of the Big Bang. And yet here, in this particular volume, the outcome had been radically different. Structure had failed to form. The cosmic web had a hole. The ghostly 8 and the 60 or so galaxies that would eventually be counted in the fuller surveys stood as witnesses to that failure. They were not evidence of normal cosmic structure. They were evidence of its absence. The very fact that they could be counted, that their population could be catalogued in a list short enough to memorize, was a testament to how strange the void truly was. In the dense regions of the universe, galaxies were too numerous to count individually. They blurred together into walls and filaments and clusters, structures that contained thousands or millions of individual objects. Here, in the Boötes Void, each galaxy was singular, isolated, a lone light in an ocean of darkness. Each one could be named. And yet, even as the surveys mapped the void's interior, even as the catalogues grew from 8 to 26 to 60, a deeper uncertainty was emerging. The question was not simply what the void contained. The question was whether the surveys could be trusted to show everything the void contained. The ghostly 8 might be the entire population of the interior, or they might be merely the brightest fraction of a much larger population, the visible tip of an iceberg that extended far below the threshold of detection. The void might be as empty as the survey suggested, or it might be filled with galaxies too faint to see. This uncertainty was not unique to the Boötes Void. It was a fundamental feature of every galaxy survey ever conducted, a limitation built into the very nature of astronomical observation. But the void made it impossible to ignore. In the dense regions of the cosmos, the uncertainty about faint galaxies was academic. Whether or not there were additional dim objects hiding below the detection threshold, the bright galaxies were so numerous that the general picture of cosmic structure would remain the same. Here, in the void, the uncertainty was existential. If the surveys were missing a significant population of faint galaxies, then the void might not be a void at all. The apparent emptiness might be an artifact of observation, not a feature of reality. To understand how this uncertainty arose, one had to understand how galaxy surveys worked in the 1980s and 1990s, the techniques that astronomers used to find and catalogue the objects that populated their maps. Every survey of that era, without exception, was a catalogue of things bright enough to trigger the instruments that astronomers had built. The technology varied: photographic plates in the earlier surveys, charge-coupled devices in the later ones. But the fundamental principle was the same. A telescope gathered light from a patch of sky. That light fell onto a detector, and if the light from a particular object was strong enough to register above the noise of the detector and the glow of the sky background, the object was recorded. If the light was too faint, the object was invisible. It did not appear in the catalogue. It did not exist as far as the survey was concerned. The key concept was surface brightness, a measure of how much light an object emitted per unit of angular area on the sky. A bright, compact galaxy might have a high surface brightness, concentrating its light into a small region that stood out clearly against the background. A dim, diffuse galaxy might have the same total luminosity, spread over a much larger area, producing a surface brightness so low that it blended into the sky and became undetectable. The distinction was crucial. Surface brightness was not the same as total brightness. A galaxy could be enormous and luminous in absolute terms, while remaining invisible to a survey that was limited by surface brightness, and every survey was limited by surface brightness. The threshold varied depending on the instrument and the observing conditions, but the limit was always there, a floor below which objects simply could not be detected. Photographic plates had their own characteristic sensitivity, a surface brightness level below which the emulsion would not respond. CCD detectors were more sensitive, but they too had limits, set by the noise inherent in the electronics and the brightness of the night sky itself. No matter how long the exposure, no matter how large the telescope, there was always a point at which the signal from a faint, diffuse object became indistinguishable from the signal of the sky background. Below that point, the object was invisible. This limitation was not neutral. It did not affect all galaxies equally. High surface brightness galaxies, compact spirals, dense ellipticals, objects where the stars were packed closely together, registered easily on the detectors. They stood out against the sky. They were the objects that filled the catalogues, the galaxies that appeared on the maps, the structures that astronomers believed constituted the universe's population. Low surface brightness galaxies, diffuse objects where the stars were spread thinly across enormous volumes were systematically invisible. They fell below the detection threshold. They did not appear in the catalogues. They did not exist in any observational sense because no one had been able to see them. The implications were profound. If low surface brightness galaxies existed in significant numbers, then every galaxy catalogue ever compiled was incomplete in a specific and directional way. The maps of cosmic structure were not wrong exactly. The bright galaxies they recorded were real, their positions accurate, their redshifts verified. But the maps were biased. They showed the universe as it appeared to instruments that could only see certain kinds of light. They did not show the universe as it actually was. Mike Disney had recognised this problem as early as 1976. Working at the University of Cambridge and later at Cardiff University, Disney had argued that traditional galaxy surveys, reliant on photographic plates, systematically overlooked low-surface brightness galaxies. The reasoning was simple. Photographic plates were only sensitive to relatively high surface brightness objects. The exposure times were limited by the motion of the sky, the stability of the telescope, the practical constraints of observing. A faint diffuse galaxy would not register on the plate because its surface brightness was too low to trigger the photographic emulsion before the exposure ended. The galaxy might be enormous, it might contain billions of stars, but if those stars were spread across a large enough area, the galaxy would be invisible. Disney's argument was theoretical at first. He could demonstrate mathematically that a significant population of low-surface brightness galaxies should exist, that the physics of galaxy formation did not prohibit the creation of diffuse objects, and that the absence of such objects from the catalogues was more likely to reflect observational bias than physical reality. But theoretical arguments were not enough to change the consensus. Astronomers trusted their data. The catalogues showed what the catalogues showed. If low-surface brightness galaxies existed in large numbers, where were they? The answer came in the mid-1980s, from an unexpected quarter. David Marlin was not a traditional astronomer. He was a photographic scientist, a specialist in the techniques of extracting information from images, in pushing the limits of what photography could reveal. He had joined the Anglo-Australian Observatory in 1975, taking responsibility for the photographic work associated with the Anglo-Australian Telescope and the UK Schmidt Telescope at Siding Spring Observatory. His job was to make the invisible visible, to coax signals out of noise, to find what had been hidden in plain sight. The techniques Marlin developed were revolutionary. Emulsion, hypersensitization, a process of treating photographic plates before exposure to increase their sensitivity. Additive RGB color processing, a method of combining black and white plates taken through different filters to produce color images that reveal details invisible in any single plate. The combination of these methods became known informally as Marlinization, a term that acknowledged how thoroughly his techniques had transformed the field. What Marlin could see in a photographic plate was not what anyone else could see. He had learned to read the faintest signals, to extract structure from what appeared to be uniform noise, to reveal objects that had been there all along but had never been detected. In 1986, Marlin made the discovery that changed everything. Working with photographic plates obtained from the UK Schmidt Telescope, he applied his enhancement techniques to a region of sky that had been surveyed many times before. What emerged from the processing was unlike anything anyone had expected. There, in a field that had been catalogued and mapped and studied for decades, was an enormous spiral galaxy that no one had ever seen. Marlin 1, as it came to be called, was the first low-surface brightness galaxy to be definitively verified. Its existence had been theoretical, now it was observational, and its properties were astonishing. The galaxy was 5 times the size of the Milky Way, a disk stretching across 650,000 light-years, dwarfing any spiral galaxy that had previously been known. But its surface brightness was so low, its stars so thinly spread across that enormous area, that it produced only about 1% as much light per unit area as a normal galaxy. It was vast and dim, a gossamer structure of stars that had been completely invisible to every survey that had looked at the region before. The discovery of Marlin 1 was not just the identification of a single unusual object, it was proof of concept. It demonstrated that low-surface brightness galaxies existed, not as theoretical constructs, not as mathematical possibilities, but as real physical objects that could be observed and measured if you knew how to look for them. And if one such galaxy existed, there was no reason to believe it was unique. The universe might be full of similar objects, enormous and diffuse and systematically invisible to the surveys that astronomers had been conducting for decades. Merlin's techniques quickly revealed additional examples. The discoveries accumulated, though the specific dates of follow-up findings like Merlin 2 are less clearly documented in the historical record. The implications were unmistakable. A new category of galaxy had been opened up, a population that had been hiding in plain sight, undetected not because it was faint in absolute terms, but because its light was spread across such enormous areas that it fell below the surface brightness limits of conventional detection. The implications for the Boötes Void were immediate. If the galaxy catalogues were incomplete, if traditional surveys had systematically missed an entire class of large diffuse objects, then the void's apparent emptiness became uncertain. The 60 galaxies that had been counted in the interior might represent the entire population, or they might represent only the brightest fraction of a much larger population of low-surface brightness objects that remained undetected. The surveys that had declared the void empty had used instruments incapable of seeing certain kinds of galaxies. What confidence could anyone have that the void was truly empty, when the instruments that had searched it were known to be blind to an entire class of objects? The discovery of low-surface brightness galaxies did not prove that the Boötes Void was populated with hidden structures. It proved only that the question was open, that the apparent emptiness could be an artifact of observation rather than a feature of reality. But that uncertainty was enough to transform the scientific debate. The void could no longer be treated as a simple observational fact, a straightforward absence of matter that theory needed to explain. It was now a question mark, a region whose true contents were unknown because the surveys that had mapped it were incomplete. What Merlin had revealed was not just a new class of galaxies, he had revealed a flaw in the observational enterprise itself, a systematic bias that had shaped every catalogue, every map, every conclusion about the universe's structure. The bright galaxies that filled the surveys were real, but they were not the whole story. Beyond them, below the detection thresholds of even the most sensitive instruments, lay a population of objects that had never been seen. How many there were, how significant their contribution to the universe's total mass, how their distribution might differ from the distribution of bright galaxies, all of these questions remained unanswered. The universe that astronomers had mapped was not the universe that existed. It was the universe that shone brightly enough to be seen. And in the Boötes Void, where the stakes were highest, where the apparent emptiness was most extreme, this uncertainty took on a particular urgency. If the void was truly empty, if the 60 galaxies in the interior represented the entire population, then it remained one of the strangest features of the observable universe, a challenge to our understanding of how structure forms and evolves. But if the void was filled with low-surface brightness galaxies, objects that had been systematically missed by every survey that had looked for them, then the apparent emptiness was an illusion. The void would not be empty at all. It would be populated by a different kind of galaxy, a kind that our instruments had not been designed to see. By the late 1980s, this question had become central to the study of the Boötes Void. The ghostly 8 had been expanded to 60 or so. The filament-like arrangement had been confirmed. The theoretical debates continued, the models were refined, the simulations grew more sophisticated, but underlying all of it was a fundamental uncertainty about what the observations actually showed. The void might be a genuine feature of cosmic structure, or it might be a feature of cosmic observation, a hole in the data rather than a hole in the universe. Merlin's ghosts haunted every conclusion. The question was no longer simply what the void contained. The question was what we had missed, what we could not see, what lay waiting in the darkness beyond the reach of our instruments. The answer would require new technology, new techniques, new ways of seeing. It would require astronomers to confront the limits of their own perception and to build tools capable of reaching beyond those limits into the dim, diffuse, hidden population of galaxies that might fill the spaces that had always appeared empty. The void remained. 330 million light-years of apparent nothing. And in that nothing, the possibility of everything we had failed to see. The possibility lingered. It settled into the literature like sediment, accumulating weight with each passing year. Through the 1990s and into the new millennium, the Boötes Void sat at the edge of cosmological attention, acknowledged, mapped to the best available precision, but fundamentally unresolved. The 60 galaxies remained, the 330 million light-years of apparent emptiness remained, and the question that Marlin's discoveries had raised, the question of what might be hiding below the detection threshold, remained as well, unanswered because it could not yet be answered. The instruments capable of settling the matter did not exist. But instruments improve, technology advances, and in the decades that followed the initial surveys, a transformation was underway in observational astronomy, a transformation that would eventually force the Boötes Void back into the spotlight, not as a solved problem, but as an open wound in the fabric of cosmic understanding. The transformation began with a simple recognition, one that had been building since Mike Disney's theoretical work in the 1970s and David Malin's photographic revelations in the 1980s. Astronomers began to accept with increasing clarity that their surveys had been designed around assumptions that might not hold. The assumption that galaxies were bright, the assumption that structure revealed itself through luminosity, the assumption that what could not be seen did not need to be counted. These assumptions had shaped every catalogue, every redshift survey, every map of the cosmic web. And they were wrong. Not entirely wrong. The bright galaxies were real, their distributions meaningful, but incomplete. Dangerously incomplete if one wanted to understand what the universe actually contained rather than merely what it displayed. The question the Boötes Void forced upon astronomy was not technical. It was philosophical. What does it mean to say that a region of space is empty? The original survey by Kirshner and his colleagues had found far fewer galaxies than expected, roughly 60 where 2,000 should have been, but the survey had targeted galaxies brighter than magnitude R16.3. Everything fainter than that threshold had been invisible, not because it did not exist, but because the survey was not designed to see it. The emptiness that had been discovered was an emptiness of bright objects. Whether it was an emptiness of objects in general remained unknown. This distinction might seem pedantic. A void is a void, one might argue. If the bright galaxies are absent, the region is still unusual, still worth explaining. But the implications ran deeper than a simple census. Cosmological models made specific predictions about what voids should contain. The cold dark matter framework, which had become the dominant paradigm by the late 20th century, predicted that voids should not be entirely empty. They should contain dwarf galaxies, small and dim, the remnants of structure formation that had failed to grow into something larger. They should contain low surface brightness galaxies, diffuse systems spread across enormous volumes, their stars scattered too thinly to produce the concentrated luminosity that traditional surveys required. The models predicted a population of objects that would be difficult to detect. And the surveys that had mapped the Boötes Void had been designed in a way that made detecting such objects essentially impossible. The tension was not between theory and observation. The tension was between theory and a particular kind of observation. An observation that was known to be incomplete. Every conclusion drawn about the void's emptiness rested on data that could not address the question being asked. It was like trying to determine whether a forest contained insects by counting only the trees. Greg Aldering, an astronomer who had worked on void populations throughout the late 1980s, captured the problem in a single haunting observation. If the Milky Way, he noted, had been located in the centre of the Boötes Void rather than in its actual position within the local group, humanity would not have known that other galaxies existed until the 1960s. The statement was not hyperbole. It was a straightforward implication of the detection limits that had governed early astronomy. The Milky Way itself would have been visible, of course. We live inside it, surrounded by its stars. But the external galaxies, the spiral nebulae that had once been mistaken for objects within our own system, would have been too faint, too distant, too scattered across too much empty space to register on the photographic plates that constituted the primary observational technology until the mid-20th century. We would have looked out at the universe and seen nothing. Not because nothing was there, but because the something that was there did not shine brightly enough to reach us. The implications extended far beyond the Boötes Void itself. If the void's apparent emptiness was partly or largely an artifact of detection limits, then what about other voids? What about the cosmic web as a whole, the filaments and walls and clusters that surveys had mapped with such confidence? how much of the universe's apparent structure was real, and how much was a reflection of what astronomers could see rather than what actually existed. The question was uncomfortable. It suggested that decades of observational cosmology might have produced maps that were systematically biased, catalogues that were missing entire populations, conclusions that rested on incomplete data. By the early 2000s, researchers began to confront this possibility directly. The approach shifted. Rather than treating the Boötes Void as a solved problem, a region of genuine emptiness that theory needed to explain, astronomers began treating it as an open question. The emphasis moved from confirming the void's existence to interrogating the observations that had defined it. Studies of dwarf galaxies in the void, conducted by researchers like Grogan and Geller around the turn of the millennium, sought to push detection limits lower, to see whether a population of dim objects might reveal itself once the instruments became sensitive enough to find them. The work was painstaking. Dwarf galaxies are intrinsically faint. They do not call attention to themselves. Finding them requires deep exposures, careful analysis, the willingness to search for objects that barely rise above the noise. The results were ambiguous in exactly the way the underlying question predicted. Some faint galaxies were found. The count rose marginally, but the void remained dramatically underdense. The question was whether the continued underdensity reflected a genuine absence of matter or simply the next level of detection bias, whether the new surveys, more sensitive than their predecessors, were still not sensitive enough to see what the void actually contained. Every map of the Boötes Void had been drawn with instruments that could not see what wasn't bright. The new maps were drawn with better instruments, but better was not the same as complete. The problem was not unique to the Boötes Void. Throughout observational cosmology, researchers were beginning to grapple with the limitations of their catalogues. The universe that had been mapped was a universe of bright objects, bright galaxies, bright stars, bright clusters. The dim universe, the diffuse universe, the universe of objects that spread their light too thinly to trigger detection algorithms, that universe remained largely unexplored. Not because no one cared about it, but because the technology to explore it had not yet matured. The photographic plates that had served astronomy for a century were giving way to digital detectors. The telescopes were growing larger, their mirrors gathering more light. The software that processed the images was becoming more sophisticated, capable of extracting signal from noise in ways that earlier generations could not have imagined. But the transformation was slow, and the old biases persisted even as the new technology emerged. What made the Boötes Void special, what kept it at the centre of this debate, was its extremity. Other voids were underdense. The Boötes Void was spectacularly underdense, an absence so profound that it strained even the most generous interpretations. If any region of space was going to reveal a hidden population of low surface brightness galaxies, it should be this one. The contrast would be sharpest here, the stakes would be highest here, and the answer, whatever it turned out to be, would have implications for the entire field. If the Boötes Void was truly empty, even when searched with the most sensitive instruments available, then the models were wrong, and something fundamental about structure formation needed to be reconsidered. But if the void was filled with dim galaxies that previous surveys had missed, then the maps themselves were wrong, and the entire observational enterprise needed to be reconsidered. Either way, the void was a test case. It was a mirror held up to astronomy's instruments, reflecting back the limitations of what those instruments could see. The Sloan Digital Sky Survey changed the scale of the inquiry. Beginning in the year 2000 and continuing through successive phases over the following decades, SDSS mapped the universe with unprecedented scope and precision. Its cameras captured images of hundreds of millions of objects. Its spectrographs measured the redshifts of galaxies by the million, placing them in three-dimensional space with an accuracy that earlier surveys could only dream of. The Boötes region fell within the survey's footprint. For the first time, the void could be mapped with instruments capable of reaching well beyond the original detection limits that had defined it. The SDSS's spectroscopic reach extended far deeper than the 1981 survey. Galaxies with Petrosian R-band magnitude brighter than 17.77 were selected for spectroscopic follow-up, a threshold that captured objects considerably fainter than the original R16.3 limit. The catalogue expanded. The count of known galaxies within and near the void grew. But the expansion told a complicated story. Finding more galaxies did not resolve the fundamental question. It only pushed the question to a fainter magnitude, a dimmer population, a class of objects that remained just beyond the new detection threshold. The completed SDSS enabled the identification of roughly 1,000 large voids across the surveyed volume, along with a sample of approximately 100,000 galaxies located within the centers of voids. The Boötes Void was no longer unique. It was part of a population, one extreme member of a class of structures that seemed to be a generic feature of the cosmic web. Voids existed. They were real. They were underdense relative to the universe's average. But the question of what they contained, the question of whether their apparent emptiness was genuine or observational, remained open even in the era of precision cosmology. The Boötes Void itself, mapped with SDSS data, remained dramatically sparse. By 1997, 60 known galaxies had been catalogued within its volume. The number did not grow substantially with the new survey. The void contained just 60 galaxies, the literature noted, significantly fewer than the approximately 2,000 expected for an area of comparable size. The original discovery had been confirmed. The emptiness was real, at least the emptiness of bright galaxies was real. But the surveys remained unable to address the population that theoretical models predicted should exist. The dwarf galaxies, the low-surface brightness systems, the diffuse objects that would be invisible even to SDSS's improved detectors. Pointed observations toward void regions failed to detect a significant population of faint galaxies. This was the finding that emerged from multiple studies through the 2000s and early 2010s. When astronomers directed their telescopes specifically toward the centers of voids, looking for the dim populations that theory predicted, they found little. The observations were deeper than previous surveys. The exposure times were longer. The analysis was more careful. And still, the voids appeared empty. Not as empty as the original surveys had suggested, perhaps. The count had risen from 60 to roughly 60, a stability that itself was telling, but far emptier than models predicted. The tension between theory and observation persisted. Cold dark matter simulations predicted that voids should contain numerous small galaxies, objects too dim to appear in magnitude-limited surveys but present nonetheless. The observations failed to find them. Either the predictions were wrong, or the observations were still not sensitive enough. There was no third option. The data and the theory could not both be correct unless one of them was incomplete. This was the intellectual crisis that defined the study of the Boötes Void in the early 21st century. The void was not simply a curiosity, an oddity at the far edges of cosmological inquiry. It was a test of fundamental assumptions about both the universe and the observations that had mapped it. Every conclusion about cosmic structure rested on surveys that were known to have biases. The biases had been characterized, studied, discussed. But characterizing a bias was not the same as eliminating it. The surveys that had mapped the Boötes Void, including the sophisticated digital surveys of the modern era, remained incapable of seeing certain kinds of galaxies. The question was how much this mattered. For some astronomers, the answer was clear. The void's emptiness was genuine, and the absence of a faint population in pointed observations confirmed that the theoretical predictions were too optimistic. The models needed to be revised. Something about the way structure formed in low-density regions differed from the standard predictions, suppressing the formation of dwarf and diffuse galaxies in ways that the simulations had not captured. This was a scientifically respectable position. It was consistent with the available data. It required no appeal to unseen populations or hidden objects. For others, the answer was equally clear but pointed in the opposite direction. The observations remained incomplete. The faint populations predicted by theory had not been found, because the instruments were not yet capable of finding them. The void's apparent emptiness was an illusion, a product of detection limits that would eventually be overcome. This too was a scientifically respectable position. It was consistent with the history of the field, with the steady expansion of the known universe as technology improved. And it carried the unsettling implication that the maps drawn by even the most advanced surveys were still maps of ignorance as much as maps of knowledge. The truth, whatever it was, lay beyond the reach of early 21st century instrumentation. The Sloan Digital Sky Survey had pushed detection limits further than ever before. But further was not far enough. The dim universe, the diffuse universe, the universe of objects that spread their light across such vast areas that they barely rose above the sky background, that universe remained hidden. The Boötes Void sat at the centre of this uncertainty, 330 million light-years of apparent nothing, challenging astronomers to explain what they could not see. And the challenge was not merely technical, it was epistemological. How do we know what exists? The question had a straightforward answer in most contexts. We observe, we measure, we catalogue. But observation had limits, measurement had thresholds, catalogues were incomplete. The universe that astronomers had mapped was the universe that had revealed itself to their instruments. What lay beyond those instruments, what existed but did not shine brightly enough to be detected, remained a matter of inference and assumption. In most regions of space, this uncertainty was manageable. The bright galaxies dominated the mass budget, the structure was clear, the maps were good enough for most purposes. But in the voids, where the bright galaxies were absent, the uncertainty became paramount. The apparent emptiness might be real, or it might be a reflection of the limits of sight itself. Aldering's observation haunted the field. If the Milky Way had been in the centre of the Boötes Void, we wouldn't have known there were other galaxies until the 1960s. The statement was a reminder of how recently humanity had become aware of the universe's true scale. Edwin Hubble had resolved the question of the spiral nebulae only a century ago, demonstrating that they were galaxies in their own right, island universes scattered across distances that defied comprehension. Before Hubble, the Milky Way was thought to be the entire universe. After Hubble, the universe exploded outward, revealing itself as a vast arena populated by billions of galaxies. But that revelation had depended on the brightness of the nearby galaxies, on their proximity, on the fact that they happened to fall within the detection limits of early 20th century photographic plates. If the local group had been embedded in a void rather than in the relatively crowded environment it actually occupied, the revelation would have been delayed by decades. The history of cosmology would have unfolded differently. The universe would have seemed smaller, lonelier, emptier than it actually was. The Boötes Void was a reminder of that alternative history. It was a region where the universe appeared as it would have appeared to observers in a less fortunate location, empty, dark, devoid of the spiral nebulae that had first revealed the cosmos beyond the Milky Way. The difference was that modern astronomers knew the void was unusual. They knew that outside its boundaries galaxies clustered in their usual profusion. The void was not the universe, it was a feature within the universe, a region where something had prevented the normal density of matter from accumulating. But within that region, the experience of observation was the same as it would have been for observers in a genuinely sparse universe. The galaxies were absent, the darkness was real, and the question of whether that darkness concealed hidden populations or reflected a genuine absence of matter remained, for now, unanswerable. The surveys continued. Through the 2010s, new instruments came online, new techniques were developed, new data accumulated. The Boötes Void remained a fixture in the literature, cited in papers on void cosmology, invoked in discussions of a large-scale structure, referenced whenever the question of observational bias arose. But the fundamental uncertainty persisted. The void had been discovered, it had been confirmed, it had been mapped with increasing precision, and still, no one could say with confidence what it actually contained. The bright galaxies were sparse, that much was clear. But the dim population, the population that theory predicted should exist, remained elusive. Perhaps it was there, hiding below the detection threshold, waiting for instruments sensitive enough to reveal it. Perhaps it was not there, and the void was genuinely empty in a way that challenged theoretical predictions. The data could not distinguish between these possibilities. What the data could do was constrain the range of plausible scenarios. The void was not teeming with bright galaxies that surveys had somehow missed. It was not filled with objects just slightly below the detection threshold that a modest improvement in sensitivity would reveal. If a hidden population existed, it would have to be dramatically fainter than anything surveys had yet detected, so faint that even the deep observations of the early 21st century could not find it. This was possible. Low surface brightness galaxies could be extraordinarily dim. Dwarf galaxies could be almost invisible, but the constraint was meaningful. The hidden population, if it existed, would have to be extreme. The alternative was equally constrained. If the void was genuinely empty, if the 60 bright galaxies were essentially the entire population, then standard cosmological models needed revision. The cold dark matter framework predicted abundant small galaxies in all environments. Their absence in the Boötes Void would indicate that something suppressed their formation, that low-density regions behaved differently than the model suggested. This too was possible. The physics of galaxy formation in voids was not perfectly understood, but the implications were significant. If voids were genuinely empty, then the relationship between dark matter and visible matter was more complex than the standard framework assumed. Either way, the Boötes Void was not simply a peculiar feature of the cosmic landscape. It was a probe of fundamental physics, a test of observational methodology, a challenge to the confidence with which astronomers claim to understand the universe's structure. The void forced a question that the field had not yet answered. What does empty really mean when we can only see what shines brightly enough to reach us? The question hung in the air as the second decade of the 21st century drew to a close. New instruments were being planned, new surveys proposed, new techniques developed. The era of low-surface brightness astronomy was dawning, driven by technologies that could reach dimmer objects than ever before. The Boötes Void would be revisited. Its contents would be mapped again, with greater sensitivity, greater depth, greater precision. But for now, the void remained what it had been since 1981. A hole in the data as much as a hole in the universe, an absence that might be real or might be an artifact of the instruments that had searched for what was not there. 330 million light-years of apparent nothing, and in that apparent nothing, the lingering possibility that the universe contained more than anyone had yet seen. The technology that would change the conversation arrived not from the great observatories, not from billion-dollar space missions, but from a row of camera lenses mounted on a wooden frame in the New Mexico desert. In 2013, two astronomers, Roberto Abraham of the University of Toronto and Peter van Dokkum of Yale University, assembled something that looked less like a scientific instrument and more like an art installation. 8 Canon telephoto lenses, the same glass a wildlife photographer might use to capture birds in flight, coupled to commercial CCD cameras and pointed at the sky. They called it the Dragonfly telephoto array, named for the compound eyes of the insect, each lens functioning like a separate optical element gathering light from the same patch of darkness. The concept was almost counterintuitive. For decades, the drive in observational astronomy had been toward larger mirrors, greater light-gathering power, more sophisticated adaptive optics to cancel the blurring of Earth's atmosphere. The Dragonfly array moved in the opposite direction. Instead of one massive lens, it used many small ones. Instead of custom optics ground to nanometer tolerances, it used mass-produced glass designed for portrait photography. The reasoning was subtle, but profound. Large telescopes with single optical paths suffer from scattered light, photons bouncing off internal surfaces, creating a faint glow that obscures the dimmest features of the sky. This scattered light is not random noise that can be averaged away with longer exposures. It is systematic, built into the architecture of the instrument itself, and it sets a floor below which no amount of integration time can probe. The Canon lenses Abraham and van Dokkum selected had been designed with obsessive attention to internal reflections. Canon's engineers, aiming to satisfy commercial photographers demanding clean contrast in backlit portraits, had developed coatings and baffles that suppress scattered light far more effectively than most astronomical optics. By combining multiple lenses, each contributing its own clean image, the Dragonfly array could achieve effective apertures comparable to small telescopes, while maintaining scattered light performance that rivaled or exceeded instruments 10 times its size. What they were hunting was a specific kind of ghost, the diffuse light that standard surveys washed away, not distant quasars or bright spiral arms or the compact cores of elliptical galaxies. Those were easy. What the Dragonfly array sought were the vast, dim hazes of stellar light spread so thin that they registered as nothing more than slight variations in the background glow, variations that other instruments dismissed as noise or atmospheric contamination or instrumental artifacts. Within 2 years of commissioning, they found what they were looking for. The target was not the Boötes Void. It was somewhere far easier to observe, the Coma Cluster, a rich aggregation of galaxies roughly 300 million light-years distant, one of the most studied structures in the nearby universe. For almost a century, astronomers had catalogued its bright ellipticals, its spiral interlopers, its compact dwarf spheroidals. The Coma cluster was supposed to be thoroughly understood. Its galaxy population was supposedly complete. The Dragonfly array revealed that it was not. In images that looked, to the untrained eye, like smudges or processing errors, the array detected 47 previously unknown objects scattered through the cluster. They were enormous, some of them approaching the diameter of the Milky Way itself, spanning tens of thousands of light-years from edge to edge. But they were almost invisible. Their central surface brightness fell below 24 magnitudes per square arc second, a measure of dimness so extreme that the objects contained perhaps 1% of the stars that a normal galaxy of their size would possess. They were the size of giants, but the luminosity of dwarfs. They were, in effect, vast empty spaces that nonetheless held together gravitationally, their sparse stellar populations marking the presence of something far more massive hiding in the dark. Abraham and Van Dockum called them ultra-diffuse galaxies, UDGs. The name was deliberately descriptive, avoiding theoretical commitments about what these objects were or how they had formed. They were simply ultra-diffuse, spread thin across enormous volumes, their light diluted to the edge of detectability. And they were galaxies, gravitationally bound systems, not chance alignments or tidal debris, but genuine structures with their own dark matter, halos holding their scattered stars in place. The 47 that Dragonfly found were just the beginning. Once astronomers knew what to look for, once the detection techniques were refined and applied to larger telescopes, the population exploded. Using the Subaru telescope in Hawaii, a team led by Jin Koda identified over 800 ultra-diffuse galaxies in the Coma cluster alone. Extrapolation suggested the true number exceeded 1,000. In a single cluster, in a region of space that had been studied for nearly a century, 1,000 galaxies had been hiding in plain sight. The implications rippled outward through the literature. If dense clusters contained such populations, what about groups? What about the field? The diffuse regions between clusters where galaxies drifted in relative isolation? What about the filaments of the cosmic web, the walls that bordered the great voids? And the question that hovered unasked in every paper, every conference talk, every late-night conversation among researchers who had spent their careers trying to understand what the universe contained. What about the voids themselves? Consider what the Dragonfly discoveries revealed about the nature of detection. For decades, surveys had been calibrated against known galaxy populations. Completeness estimates assumed that galaxies followed certain patterns: a bright core surrounded by fainter outskirts, a surface brightness profile that peaked at the center and declined predictably toward the edges. Standard algorithms searched for these patterns, flagged them as candidate objects, passed them to classification pipelines. What the ultra-diffuse galaxies demonstrated was that an entire category of object could evade this detection logic. If a galaxy had no bright core, if its surface brightness was essentially flat across its entire extent, hovering just above the sky background, the algorithms would dismiss it as a fluctuation in the background itself. The galaxy would be there, in the data, but the analysis would not recognize it as a galaxy. This was not a failure of the data, it was a failure of the assumptions built into the analysis. And the ultra-diffuse galaxies were not merely academically interesting, their physical properties were extraordinary. Dynamical studies, measurements of how their sparse stars moved under the influence of gravity, suggested that some of these objects were almost entirely dark matter. Stellar mass accounted for perhaps 2% of the total. The remaining 98% was invisible, detectable only through its gravitational effects on the handful of stars that had managed to form. These were not galaxies in the conventional sense, not the luminous structures that had defined the discipline since Edwin Hubble's work in the 1920s. They were dark matter halos with a smattering of stars, faint traces of enormous unseen masses. If such objects could hide in the dense environment of a galaxy cluster, if they could form and persist within a few 100 million light-years of Earth, in one of the most thoroughly observed regions of the sky, then the question of what filled cosmic voids became suddenly urgently uncertain. The Dragonfly array was expanded. In 2016, it grew from 10 lenses to 2 separate clusters of 24 lenses each, increasing its light-gathering power and its ability to probe ever fainter surface brightness levels. Other groups developed similar techniques. The field of low-surface brightness astronomy, which David Malin had pioneered decades earlier through his photographic amplification methods, entered a new era of systematic digital exploration. And the theorists were not idle. While the observers searched for what their instruments might have missed, the simulators were building universes on supercomputers, trying to understand what should be there in the first place. The question of cosmic voids had evolved from a simple puzzle, why are there holes in the galaxy distribution, into a sophisticated probe of cosmological physics. Voids were no longer embarrassments to be explained away, they were tools. Nico Hermaus and his collaborators approached voids as statistical ensembles, analysing their size distributions, their shapes, their clustering properties. What they found was remarkable. Voids displayed self-similarity across scales. Small voids resembled large voids. The statistical properties of the void population followed patterns that emerged naturally from the mathematics of gravitational collapse operating on primordial density fluctuations. This self-similarity made voids extraordinarily clean probes of the underlying physics. Unlike galaxy clusters, which were complicated by baryonic processes, gas cooling, star formation, supernova feedback, the violent astrophysics of visible matter, voids were dominated by the simplest possible dynamics, gravity and dark energy. Alice Pisani, working with dozens of collaborators across multiple institutions, extracted cosmological constraints from void statistics using data from the Baryon Oscillation Spectroscopic Survey. Their results were striking. Voids, these empty regions that had seemed like absences rather than presences, provided some of the tightest constraints to date on the universe's matter content and dark energy properties. The emptiness was not a lack of information, it was information of a different kind. And what the theorists understood about voids was this: they are not static. A cosmic void is not a hole punched in a uniform distribution and then frozen in place. A void is a dynamic object, an expanding bubble driven by the peculiar physics of under-dense regions in an accelerating universe. Consider a region of space that, in the early universe, happened to contain slightly less matter than average. Not dramatically less, the primordial variations were tiny, 1 part in 100,000, but enough that the gravitational pull toward the centre of that region was weaker than the pull toward neighbouring regions. Over cosmic time, matter drifted away. Galaxies that might have formed in the low-density region were pulled toward the denser surroundings, drawn into the filaments and walls of the cosmic web. The underdense region became more underdense. It expanded, not because space within it was stretching faster than elsewhere. Space expanded everywhere at the same rate, but because its contents were evacuating, draining toward the denser structures around it. In a universe without dark energy, this process would eventually slow and perhaps reverse as the overall expansion of space decelerated. But in the universe we inhabit, dark energy dominates. The expansion accelerates. And in voids, where the gravitational braking from matter is weakest, the effects of dark energy are most pronounced. Voids become, in a sense, the most dark energy-dominated environments in the cosmos. They are ideal laboratories for studying the properties of this mysterious component that comprises some 70% of the universe's total energy density. The Boötes Void, from this perspective, was not merely an anomaly in the galaxy distribution. It was a billion-year-old process caught in action. Matter had been draining from its interior for cosmic ages, piling up in the walls that surrounded it, leaving behind whatever objects were either too isolated to be pulled away or formed too late to escape. The void was not simply empty, it was evacuated, and it was still growing, still expanding, still driving its contents outward to the boundaries. This dynamic picture raised new questions about the galaxies that remained inside. The 60-odd objects that surveys had found within the Boötes Void, were they the survivors of an ancient population, left behind as their neighbours were drawn to the walls? Were they latecomers, objects that formed from residual gas after the main evacuation was complete? Were they falling in from the walls themselves, captured in trajectories that would eventually carry them through the void's interior? Or were they something else entirely, objects whose formation and evolution had proceeded differently in the extreme low-density environment of the void's heart? The theorists could not yet say. The simulations could grow voids and track their contents, but matching the detailed properties of individual observed voids remained difficult. The Boötes Void was one object. Statistical comparisons required populations, and the observational challenges of measuring the properties of the faint galaxies within the void compounded the difficulty of understanding their origins. But the observers were closing in, armed now with the knowledge that their surveys had been systematically blind to an entire category of object. The question that hung over the field was sharp and specific. If galaxy clusters contained hundreds of ultra-diffuse galaxies that had escaped detection for decades, might the Boötes Void contain a similar population? The parallels were not exact. A galaxy cluster is a dense environment, its gravitational potential well-trapping hot gas and accelerating encounters between galaxies. The processes that might form ultra-diffuse galaxies and clusters, tidal stripping, harassment by neighbours, ram pressure removal of gas, did not obviously apply in the extreme low-density environment of a void, but other formation channels were possible. Perhaps ultra-diffuse galaxies formed from primordial halos that never accumulated enough gas to form stars efficiently. Perhaps they were the natural outcome of galaxy formation in low-density environments, where gas collapsed slowly and star formation sputtered rather than roared. Perhaps the void was full of them, their faint surface brightness hiding them from even the deep surveys that had mapped the region over the previous decades. No one knew. The instruments that had found ultra-diffuse galaxies in the Coma cluster had not yet turned their attention to the Boötes Void with comparable depth and sensitivity. The void was larger, more distant in portions, and spread across more sky. A systematic survey would require significant telescope time and careful analysis. Such surveys were being planned, proposed, negotiated through the slow processes of telescope allocation committees. But the data did not yet exist. What existed was a possibility. A haunting, unresolved possibility that cut to the heart of the documentary question the Boötes Void had posed since 1981. We had always asked, what does the void contain? Now the question fractured into two distinct versions, each pointing toward a different universe. In one version, the Boötes Void was what it appeared to be, genuinely cosmically empty. The 60 galaxies that surveys had found represented essentially the complete population. The theoretical predictions of abundant dwarf galaxies filling all environments were wrong, at least for extreme voids. Something about the low-density environment, perhaps the slow collapse times, perhaps the lack of mergers that trigger star formation, perhaps some subtle physics of gas cooling that operated differently in isolation, had suppressed galaxy formation. The void was a bubble of almost nothing, a 330 million light-year sphere in which the universe had simply failed to build the structures it built everywhere else. This was an extraordinary claim. It challenged the standard understanding of dark matter, which predicted that small halos should form abundantly in all environments. It suggested that the relationship between dark matter and visible matter was more contingent, more dependent on environmental factors than the cold dark matter framework assumed. If this version was true, the Boötes Void was not just a curiosity. It was a probe of fundamental physics, a natural experiment that revealed processes invisible in denser regions. In the other version, the Boötes Void was full. Not full in the way a galaxy cluster is full, not crowded with bright spirals and massive ellipticals. Full in the way a twilight forest is full of moths, populations invisible against the background until you know how to look. Perhaps the void contained hundreds or thousands of ultra-diffuse galaxies, their surfaces so faint they registered as nothing more than noise in existing surveys. Perhaps it harboured dwarf galaxies dimmer than anything yet catalogued, their few thousand stars lost in the glare of foreground contamination. Perhaps the dark matter halos were there, exactly as cold dark matter predicted, but the visible traces, the stars that would reveal their presence, were so sparse that no instrument had yet detected them. Greg Aldering's observation from decades earlier echoed through this possibility. If the Milky Way had been located at the centre of the Boötes Void, humanity would not have discovered other galaxies until the 1960s. The faint galaxies at the edge of detectability, the Magellanic Clouds, the dwarf spheroidals of the local group, would have been invisible across the 100 million light-year distances that would have separated them from an observer in the void's heart. The universe would have seemed empty not because it was empty, but because the instruments were not yet capable of seeing what was there. The Dragonfly Array had proven that such systematic blindness was not hypothetical. It was real. It had persisted for decades in one of the most studied regions of the sky. The Coma cluster's 1,000 ultra-diffuse galaxies had been there all along, waiting for someone to build an instrument capable of seeing them. What else was waiting? The honest answer, the answer that the observational literature was slowly, carefully converging upon, was that no one yet knew. The surveys that had probed the Boötes Void were deeper than the original 1980s work. They had pushed from 16th magnitude to 17th magnitude and beyond. They had found a few additional objects, raising the count from the original handful toward the current 60. But they had not reached the surface brightness levels that the Dragonfly array could achieve. They had not been designed to detect ultra-diffuse objects. Their analysis pipelines had been built on assumptions that excluded precisely the category of object that might fill the apparent emptiness. This was not a criticism of the earlier work. It was an acknowledgement of how science proceeds. Each generation of instruments reveals phenomena that previous generations could not detect. Each expansion of parameter space opens new windows on reality. The question was not whether earlier surveys had failed. The question was whether the new generation of instruments, armed with new understanding of what might be hiding in the dark, would finally resolve the ambiguity that had surrounded the Boötes Void since its discovery. The two versions of the Void implied profoundly different universes. In the empty void, the cosmos was simpler than cold dark matter suggested. Galaxy formation was not inevitable in dark matter halos. Some environments were genuinely barren, their potential wells filled with dark matter that had never sparked into visible light. The relationship between the invisible scaffolding of the universe and the luminous structures that astronomers observed was loose, contingent, dependent on factors that theory had not yet fully captured. In the full void, the cosmos was richer than observations had revealed. The surveys that had mapped the universe for decades had been surface skimming, cataloguing the bright objects while missing vast populations of diffuse, faint, nearly invisible structures. The true galaxy population might be orders of magnitude larger than current estimates. The dark matter framework would be vindicated, but the observational census would require dramatic revision. Either possibility was extraordinary. Either would reshape understanding of what the universe contained and how it had evolved. And the data that would distinguish between them did not yet exist. The Boötes Void hung in the literature as it had since 1981, a hole in the data as much as a hole in the universe. But now the stakes were clearer. Now the technology existed, or nearly existed, to answer the question that Robert Kirshner's team had inadvertently posed when they found 3 galaxies where they expected 100. What does empty really mean? The answer was out there, hiding in 330 million light-years of darkness, waiting to be gathered by instruments sensitive enough to see what no survey had yet revealed. Waiting for someone to point the right lenses at the right patch of sky and capture the photons that would settle the question. Waiting for the data that would show whether the void was a genuine absence or an artifact of the instruments that had searched for what was not there. The technology exists. That is the quiet revolution that separates this moment from every earlier chapter of the story. For decades, the Boötes Void remained ambiguous because the instruments capable of resolving the ambiguity had not been built. The photographic plates of the 1980s could not reach the surface brightness levels where ultra-diffuse galaxies lurked. The digital surveys of the 1990s and 2000s pushed deeper in apparent magnitude but retained analysis pipelines, calibrated to find objects with bright cores and steep luminosity profiles. The Dragonfly array proved that purpose-built instruments could reveal entire populations of galaxies that had been invisible to everything that came before. The principle was established. The question was no longer whether such objects could be detected. The question was whether anyone would point the right instrument at the Boötes Void and look. The specifications of such a survey are not mysterious. They can be written down. A definitive census of the Void's interior would require a wide-field imager capable of reaching surface brightness levels below 24 magnitudes per square arc second, the threshold where ultra-diffuse galaxies become detectable against the noise of the sky background. It would need to cover a substantial fraction of the Void's angular extent, which spans roughly 15 degrees across the northern sky, an area larger than 1,000 full moons. It would require hundreds of hours of exposure time, stacked and combined with exquisite precision, to beat down the noise and reveal the faintest structures. The data reduction would need pipelines designed specifically to detect extended, low-contrast objects rather than the point sources and compact profiles that traditional astronomy software was optimized to find. None of this is beyond current capability. The Dragonfly array demonstrated the approach on smaller scales. The Subaru telescope's hyper-suprime cam has achieved the required depth in targeted fields. The infrastructure exists, the techniques are understood. What has been lacking is the decision to deploy those resources against the specific question that the Boötes Void poses. On the 30th of June, 2026, the Vera C. Rubin Observatory began full survey operations in the Chilean Andes. The Legacy Survey of Space and Time, the LSST, represents the most ambitious wide-field imaging campaign ever undertaken. Over 10 years, the survey will capture approximately 800 images of each location in the southern sky, building up exposure depth through repeated visits that will eventually reach surface brightness levels competitive with the deepest targeted observations. The survey area does not naturally include the northern constellation of Boötes, which rides high in skies visible from Kitt Peak and Palomar rather than Cerro Pachón. But the observatory's capabilities establish a new baseline for what systematic surveys can achieve. The LSST will catalogue billions of galaxies, including populations of low surface brightness objects that previous all-sky surveys could not detect. It will provide, for the southern hemisphere at least, the kind of complete census that the Boötes Void has never received. The question of whether to turn equivalent resources toward the void itself remains unanswered. It is a question about priorities, about telescope time, about which mysteries the astronomical community considers worth solving. Every major observatory operates under constraints. Telescope time is allocated through competitive processes. Proposals must justify their scientific value against alternatives. A deep survey of the Boötes Void would consume resources that could otherwise be devoted to studying active galactic nuclei, or mapping the cosmic microwave background, or characterizing exoplanet atmospheres. The void competes for attention with every other unanswered question in astronomy, and for 4 decades it has consistently lost that competition. This is not a failure of imagination. It is a feature of how science allocates its limited resources. Questions that seem likely to yield definitive answers attract more attention than questions whose outcomes remain uncertain. A survey that might find a hidden population of ultra-diffuse galaxies, or might confirm that the void is genuinely empty, offers ambiguous expected value. The discovery space is real, but the probability of discovery is unknown. Telescope allocation committees, faced with proposals whose outcomes are more predictable, have historically chosen the safer investments. The result is a curious lacuna in the observational literature. The Boötes Void has been known for 45 years. It remains one of the largest coherent structures in the mapped universe. Its implications for cosmology are profound, regardless of whether it is genuinely empty or filled with undetected galaxies. And yet no survey has been conducted with the explicit purpose of answering the question that its existence poses. The 60 galaxies catalogued in its interior were found, incidentally, through surveys designed for other purposes. The void has been observed, but it has not been targeted. It has been acknowledged, but it has not been prioritized. Greg Aldering's thought experiment returns with renewed force. If the Milky Way sat at the center of the Boötes Void, humanity would not have known that other galaxies existed until the 1960s. The nearest bright neighbor would have been hundreds of millions of light-years away, far beyond the reach of the instruments that Edwin Hubble used to resolve Andromeda into individual stars. The Great Debate of 1920 would never have occurred, because there would have been nothing visible to debate. The island universe hypothesis would have remained forever untestable. Cosmology would have developed along entirely different lines, if it had developed at all. This scenario is not merely hypothetical. It describes in compressed form the situation that any civilization inside the Boötes Void would actually face. If such civilizations exist, if the 60 known galaxies harbour technological species looking outward at their empty sky, they would experience the universe as fundamentally lonelier than we do. Their Hubble would have found nothing. Their Vera Rubin would have no rotation curves to measure, no spiral arms to photograph, no evidence that the cosmos extended beyond their own isolated system. They might eventually develop instruments capable of detecting the distant walls of the void, the great filaments of galaxies that mark its boundaries, but that detection would come late in their technological development, if it came at all. The thought experiment illuminates something about our own situation. We look outward from a position of relative cosmic richness. The local group contains dozens of galaxies within a few million light-years. The Virgo cluster glows in our spring sky, a concentration of thousands of systems close enough for detailed study. The cosmic web surrounds us with structure, with neighbours, with evidence of the universe's vast fertility. Our instruments were calibrated against this abundance. Our theories were developed to explain it. When we found the Boötes Void, we interpreted it against the backdrop of everything else we had seen, as an anomaly, an exception, a hole in an otherwise continuous fabric. But what if our position is the exception? What if the cosmic web's nodes and filaments, the clusters and superclusters that dominate our view, represent the minority of the universe's volume? Voids, after all, occupy far more space than the dense regions. The Sloan Digital Sky Survey found roughly 1,000 voids in its survey volume, and the volume of empty space exceeded the volume of concentrated structure by substantial margins. The typical location in the universe is not near a galaxy cluster. It is somewhere in the middle of a void, surrounded by millions of light-years of apparent emptiness. If observers are distributed according to where galaxies actually form, most observers might find themselves in regions richer than average, but the inverse is also possible. The question of what the universe looks like depends on where you happen to be standing when you look. The Boötes Void is a reminder that the universe we observe is not the universe as it is. It is the universe as it appears from our particular vantage point, filtered through instruments with particular sensitivities, interpreted through theories developed to explain particular phenomena. Every observation is an act of selection. Every catalogue excludes more than it includes. The 3 galaxies that Robert Kirshner's team found in 1981 were not the only objects in their survey field. They were the only objects bright enough, compact enough, and central enough to trigger the detection algorithms that the team was using. Everything else was present in the data. The photons were captured on the photographic plates, but it was not extracted, not catalogued, not counted. This is the fundamental limitation of observational science. We can only count what we can see, and we can only see what our instruments are capable of detecting, and our instruments are always calibrated against assumptions about what we expect to find. The Boötes Void violates those assumptions. It presents a region where the expected population does not exist, or does not exist in the form that our instruments were designed to detect. The ambiguity cannot be resolved by theoretical argument. It can only be resolved by building instruments sensitive enough to see what previous instruments missed, and pointing them at the void for long enough to gather the photons that would answer the question. The astronomers who study ultra-diffuse galaxies understand this. Alison Merritt, Peter van Dokkum, Roberto Abraham and their collaborators have built careers on the premise that the universe contains more than traditional surveys revealed. Their work on the Coma cluster demonstrated the principle. Their instruments proved that entire populations of galaxies had been hiding in plain sight, overlooked because their surface brightness fell below the detection thresholds of standard analysis. They know what the Boötes Void might contain. They know how to look for it. The question is whether the resources will be allocated, whether the proposals will be approved, whether the telescope time will be granted. The void has waited for 45 years. It can wait longer. The photons that would answer the question are travelling through space right now, ancient light from galaxies that may or may not exist in the void's interior, heading toward Earth at 300,000 kilometers per second. Some of those photons will arrive tonight, falling on the mirrors of telescopes pointed in other directions, absorbed by detectors calibrated to find other things. Some will arrive next year, or next decade, or next century. They will keep arriving as long as the sources that emit them continue to shine, which for ultra-diffuse galaxies could be billions of years. The question is patient. The universe does not care when we answer it, but we might care. The Boötes Void is not merely an astronomical curiosity. It is a test case for how science decides what counts as worth knowing. The void forces a question that extends beyond astronomy into epistemology, into the philosophy of scientific practice. How do we allocate resources to investigate phenomena whose existence is uncertain? How do we weigh the value of confirming an absence against the value of discovering a presence? How do we justify spending hundreds of hours of telescope time on a region that might yield nothing, when other regions promise certain returns? These questions have no clean answers. Science is a human enterprise conducted by people with limited time and resources, competing for attention and funding in a world that demands results. The Boötes Void offers no guaranteed payoff. A deep survey might find exactly what current surveys have found, a handful of galaxies scattered through an enormous volume of nearly empty space. The void might be genuinely empty, and a definitive survey would simply confirm what has been suspected for decades. That confirmation would have scientific value, but it would not have the drama of discovery. It would close a question rather than open new ones, or the survey might find something extraordinary. It might reveal a population of ultra-diffuse galaxies carpeting the void's interior, thousands of faint systems that had been invisible to every previous instrument. It might vindicate the cold dark matter model in spectacular fashion, demonstrating that the relationship between dark matter halos and visible galaxies extends even into the most extreme environments. It might force a complete reassessment of the cosmic census, suggesting that the universe contains far more galaxies than anyone had imagined. The discovery space is real, and the potential implications are profound. The uncertainty is the story. The not knowing is the condition that defines our relationship to the Boötes Void and has defined it since 1981. When Robert Kirshner and his collaborators, Augustus Oehmler Jr., Paul Schechter, Stephen Schechtman, published their discovery in the Astrophysical Journal Letters, they described what they had found: a region of space with far fewer galaxies than expected. They did not claim to have explained it. They did not assert that the void was genuinely empty rather than apparently empty. They presented data, and the data showed an absence where an abundance had been predicted. The interpretation remained open. It remains open still. The subsequent surveys, the 1987 follow-up, the work by Rood and his collaborators, the Sloan digital sky surveys passes through the region, have refined the numbers but have not resolved the ambiguity. 60 galaxies instead of 2,000. Less than 3% of the expected density, the most extreme underdensity in the local universe. These facts are established. What they mean is not. The tube-shaped strand of galaxies running through the void's centre suggests a particular history. Most of the 60 known systems cluster along this filament, rather than spreading uniformly through the volume. This distribution implies that the void did not form as a single event, a spherical bubble blown in the cosmic medium by some unknown force. Instead, it may have grown from several smaller voids that merged over cosmic time, the way soap bubbles combine when their walls thin and rupture. The filament would then represent the remnant of a former wall, a region that was once denser than average, but has been stretched and diluted as the surrounding voids expanded and coalesced. This picture is consistent with the lambda CDM cosmological model, which predicts that voids grow through expansion and merger. The model also predicts that voids should contain substantial populations of low-mass halos, concentrations of dark matter that never accumulated enough gas to form visible galaxies, or that formed galaxies too faint and diffuse to detect with current instruments. These phantom halos would be invisible to optical surveys, but would reveal themselves through gravitational effects, through weak lensing measurements, through dynamical studies of the few visible galaxies that orbit within the void's volume. Such studies have been attempted. The results are ambiguous. Some analyses suggest that the void's interior contains less dark matter than expected, reinforcing the picture of genuine emptiness. Others suggest that the dark matter is present but has simply failed to form visible structures, supporting the picture of a full void whose contents remain hidden. The data does not yet distinguish between these possibilities. The samples are too small, the uncertainties too large, the systematic errors too difficult to control. The void remains a hole in our knowledge as much as a hole in the universe. When we say that it is empty, we are describing our observations, not the underlying reality. The observations are real. Kirshner's team really did find 3 galaxies where they expected 100, and subsequent surveys really have found only 60 in a volume that should contain 2,000. But observations are always filtered through instruments and assumptions. The instruments have improved since 1981. The assumptions have begun to shift, as the discovery of ultra-diffuse galaxies has revealed how much previous surveys might have missed. But the definitive test has not been conducted. The question remains open. Perhaps it will remain open indefinitely. Science does not guarantee answers. It does not promise that every question will be resolved, that every mystery will be solved, that every ambiguity will be clarified. Some questions persist because the data required to answer them is too expensive to gather, or because the phenomena involved are too rare to study statistically, or because the scientific community simply decides that other questions are more pressing. The Boötes Void might become one of these persistent mysteries, a feature of the astronomical landscape that everyone acknowledges but no one quite gets around to explaining. Or perhaps the next generation of instruments will settle the matter. The Rubin Observatory's LSST will transform wide-field astronomy. Future space telescopes will achieve sensitivities that ground-based instruments cannot match. The techniques pioneered by the Dragonfly Array will be scaled up and applied to larger regions of sky. Eventually, someone will point the right instrument at the Boötes Void and gather the data that would show what is actually there. When that happens, if that happens, the answer will seem obvious in retrospect. It always does. The discovery of ultra-diffuse galaxies in the Coma Cluster seems inevitable now, a straightforward consequence of building instruments sensitive to low surface brightness emission. But before the discovery, it was not obvious at all. The galaxies had been invisible for decades, overlooked by surveys that should have detected them, missed by astronomers who were looking at the same data. The detection required not just better instruments, but a different way of thinking about what galaxies could be, what shapes and luminosities and surface brightnesses were possible. The discovery changed the question as much as it answered it. The same may be true for the Boötes Void. The question we are asking, is it empty or full, may not be the right question. The categories of empty and full may be too simple to capture the reality of a 330 million light-year region of space containing 60 visible galaxies and an unknown number of invisible ones. The void may be something else entirely, something that we do not yet have the concepts to describe, something that will only become clear when we have gathered the data that would force us to develop new categories. This is the deepest lesson of the void, the one that extends beyond astronomy into the nature of scientific understanding. We do not know what we do not know. The categories we use to organize our observations are not given by nature. They are constructed by us, shaped by our instruments and our theories and our expectations. The void challenges those categories. It presents a phenomenon that does not fit cleanly into our existing frameworks. It asks us to consider the possibility that our frameworks are incomplete. In 1981, a team of astronomers converted photographic survey data into a three-dimensional map using redshift measurements. Each galaxy was placed at its true distance, rather than just its position on the page. A flat photograph became a volume of space, and in that volume, a gap opened up. The Great Nothing took shape in the data, 330 million light-years of apparent emptiness where the cosmic web should have been. The discovery was a product of technique as much as observation. Without redshift measurements, the void would have remained invisible, its galaxies indistinguishable from background objects at greater distances. The technology made the absence visible, transformed a featureless survey field into a three-dimensional puzzle. The technology of our own era makes other things visible. The Dragonfly Array reveals ultra-diffuse galaxies. The LSST will reveal transient phenomena and faint moving objects, and the subtle distortions of gravitational lensing. Future instruments, not yet built, will reveal things we cannot currently imagine. Each advance in sensitivity opens a new window, and through each window the universe appears different than it did before. The Boötes Void will look different through these new windows. The question is what we will see when we finally look through them with sufficient attention, sufficient patience, sufficient willingness to find whatever is actually there. The void waits. It has been waiting since before there were eyes to see it, before there were planets to host those eyes, before there were galaxies to illuminate those planets. It formed in the first billion years after the Big Bang, when the density fluctuations that seeded all cosmic structure were first separating into overdense and underdense regions. It grew through the expansion of the universe, through the merger of smaller voids, through the slow evacuation of matter toward the surrounding filaments and walls. It became, over 13 billion years, the structure that Robert Kirshner's team discovered in 1981, a hole in the cosmic web, a region of profound emptiness, a challenge to our understanding of how galaxies form and where they choose to form. It will keep waiting. The photons that could answer our questions are already travelling toward us, have been travelling for hundreds of millions of years, will arrive whether we build the instruments to capture them or not. The void does not require our attention. It does not need to be understood. It simply is a feature of the universe, a consequence of the physics that governs cosmic structure, a region of space where far fewer galaxies formed than our models predicted. When we said it was empty, We were describing ourselves. We were describing the limitations of our instruments, the assumptions built into our analysis, the categories we use to organize our understanding of what the universe contains. The void is not a statement about the universe. It is a question about how we know what we know and what we might be missing, and whether the tools we have built are adequate to the task of comprehending a cosmos that extends far beyond our ability to perceive it directly. The question remains open. It remains enormous. It remains, after 45 years, still waiting to be answered. And somewhere in 330 million light-years of darkness, the photons continue their journey toward us, carrying information about structures that may or may not exist, about galaxies that may or may not have formed, about a universe that may be richer or emptier than anything we have yet imagined. They have been travelling since before humanity existed. They will arrive whether we are watching or not. The only question is whether, when they finally reach us, we will have built the instruments capable of catching them and the understanding capable of comprehending what they reveal. The Boötes Void is not an answer. It never was. It is the question itself, written in 330 million light-years of apparent emptiness, inscribed in the distribution of 60 ghostly galaxies along a tube-shaped strand through the darkness, encoded in the photons that left those galaxies hundreds of millions of years ago and are still falling toward us now. It asks, what does empty really mean, when we can only see what shines brightly enough to reach us? We do not know yet. But for the first time in 4 decades, we have the tools that might tell us. The question is whether we will choose to ask.